A technician walks into a house, fixes the actual problem in 11 minutes, then spends 47 minutes being lectured about things that are not problems. That technician is now selling insurance. Here are 71 reasons why. 1. Your house should be the same temperature in every single room at all times, and any variation whatsoever is proof the technician installed something wrong. That is the complaint, delivered with the confidence of someone who has never once opened a physics textbook. The hard truth is that uniform room-to-room temperature in a residential home is physically impossible from a single central system without a fully zoned multi-unit setup. And even then, you are working with approximations, not guarantees. Heat stratifies. Warm air rises, cool air sinks, and a two-story home can carry a 5 to 10 degree natural variance between floors with a perfectly functioning system. This is thermodynamics, not a warranty issue. Room size, ceiling height, insulation quality, window count, and whether your windows face south or north all independently determine how any given room receives and holds conditioned air. The ductwork was designed for balanced airflow across the whole structure using the ACA manual J load calculation, the industry standard that accounts for the entire building, not surgical precision per bedroom. A correctly sized, correctly installed system will still produce room variance because the rooms are physically different from each other. The Department of Energy has confirmed that even in well-sealed, well-insulated homes, a 2 to 4 degree variance between adjacent rooms is completely normal and acceptable performance. The fix for true room-by-room control is a multi-zone mini-split system that costs 3 to 5 times more than a standard central unit. You are demanding Formula One performance from a system that was never built to be a Formula One car, and then filing a complaint when it drives like the sensibly priced family vehicle it actually is. 2. You are absolutely certain your technician is lying about the refrigerant because you have done your research and your research has concluded that refrigerant is a closed loop. It does not get used up, and therefore any claim that your system is low must be a creative fiction designed to extract money from reasonable, innocent people like yourself. Refrigerant absolutely disappears through leaks. A low refrigerant reading is not a technician's improvised storytelling. It is a diagnostic finding with a specific physical cause, a breach somewhere in the sealed system in the form of a cracked fitting, a corroded coil, a faulty Schrader valve, or a pinhole in the copper line set. The EPA's Section 608 regulations under the Clean Air Act make it illegal for technicians to intentionally vent refrigerants into the atmosphere, and falsely adding refrigerant to a non-leaking system would be both pointless and professionally traceable. Licensed technicians document charge weight because their certification depends on it. R22, the refrigerant phased out of production in 2020 under the Montreal Protocol, ran as high as $100 per pound on the secondary market in its final years, making a low refrigerant diagnosis genuinely expensive and genuinely real. Modern refrigerants require manifold gauge sets and EPA certification to handle, meaning the person charging you for refrigerant has the paperwork, the instruments, and the legal accountability to back up that line on your invoice. A system that keeps running low without a replenishment history is telling you exactly one thing. Something is leaving the system. Physics does not run a charity. Telling your technician refrigerant cannot disappear because the loop is closed is the mechanical equivalent of telling your plumber water cannot leak because your pipes are also closed loops. The leak is real, the denial is not a counter-argument. 3. The air filter in your home is something you treat like a historical artifact, something to be preserved, occasionally acknowledged, and never touched. And you are genuinely baffled when the technician pulls out what appears to be a felt wall hanging that was once, in a better life, an air filter. A severely clogged filter is not a minor housekeeping oversight you can cheerfully apologize for. It is the single most common cause of HVAC system failure, reduced efficiency, frozen evaporator coils, and compressor burnout, all of which are completely preventable and entirely your responsibility. The standard industry recommendation for 1-inch filters is replacement every 30 to 90 days depending on your household. Pets, smokers, and allergy sufferers land at the 30-day end of that range. This is printed on the filter packaging that came with the filter you installed and then forgot about for 2 years. A clogged filter increases static pressure inside the duct system, airflow to the evaporator coil drops. The coil surface temperature falls below freezing, and the resulting ice buildup shuts the system down completely. A direct, unbroken causal chain from a $5 filter to a $500 service call. Restricted airflow also forces the blower motor to draw more electrical current and generate excess heat, degrading motor windings over time. The Department of Energy estimates that replacing a clogged filter can improve HVAC's energy efficiency by 5 to 15%, a measurable difference that shows up on your monthly utility bill. The air filter is the one maintenance item in the entire system that was specifically designed to be handled by you, the homeowner, between professional visits. It is the one job, the single delegated task. Changing it every few years is the HVAC equivalent of changing your car's oil every 60,000 miles and then standing in the parking lot genuinely puzzled about why the engine seized. 4. You arrive home to a house that feels warm, walk directly to the thermostat and slam it down to 60 degrees with the full expectation that this aggressive number will cause the system to surge into action like a rocket booster and cool the house at some kind of accelerated, proportional rate that reflects the urgency of your discomfort. A central air conditioning system outputs exactly one speed of cooling regardless of what temperature you punch into the thermostat. Setting it to 60 degrees does not make the air colder, faster, or more powerful. It only determines where the system eventually stops. And in most cases, 60 degrees is a temperature your standard residential system cannot physically achieve, so it will simply run without ever stopping, which is not the turbo mode you were imagining. A standard single-stage air conditioner operates in one mode, fully on or fully off. When it runs, it moves the maximum BTUs it was designed to move. The rate of heat removal from your space is governed by the system's rated BTU capacity and the temperature difference between the indoor air and the refrigerant, neither of which changes based on your thermostat input. Modern variable speed systems can modulate compressor output, but even these have a maximum capacity ceiling, and they ramp up automatically in response to load conditions, not because you typed an extreme number. Setting the thermostat to 60 degrees in an 85-degree house causes the system to run in long, unbroken cycles, which can freeze the evaporator coil in high humidity conditions and turn your temporary discomfort into a multi-hour shutdown. The Electric Power Research Institute has documented that extreme thermostat setbacks drive unnecessary energy consumption and peak demand strain. Pressing the elevator button 17 times does not make the elevator arrive faster. The mechanism was already doing everything it could before your fourth press. 5. Your functioning HVAC system makes sounds, clicks, hums, whooshes, the occasional settling tick from the ductwork, and you have decided each of these constitutes evidence of imminent structural collapse, documenting them in a running list you present to the technician with the organized energy of someone building a legal case. HVAC systems are mechanical systems with motors, compressors, fans, and refrigerant under pressure, and they make noise because that is what mechanical systems do. The clicking you hear at startup and shutdown is the contactor relay switching, an electrical component that engages the compressor every single time the system cycles for its entire service life. The whooshing from the vents is air moving through sheet metal ductwork, which was never acoustically engineered because that was not the assignment. The gurgling you hear briefly after shutdown is refrigerant pressure equalizing between the high and low sides of the system. Thermodynamics, completing a cycle the way it was designed to. The ductwork popping and ticking as it expands and contracts with temperature changes is metal behaving exactly as metal behaves when temperature changes. Condenser units operate with fan motors running at over 1,000 RPM and compressors vibrating at 60 Hz, producing sound levels that typically range from 60 to 75 decibels at 3 feet, roughly the volume of a normal conversation. Genuinely alarming sounds have distinct, specific characteristics. Metal on metal grinding indicates bearing failure. Loud, persistent banging means something is loose inside the air handler. A high-pitched, sustained squeal points to a specific mechanical or refrigerant issue. These are diagnostically meaningful and qualitatively different from operational sounds. Demanding a silent HVAC system is like demanding a silent dishwasher. The mechanism of the thing is the noise. If your house is completely silent when the system runs, either it is not running or you have paid for something genuinely remarkable. 6. Closing the vents in your unused rooms is your proudest energy-saving innovation, the one household decision you feel genuinely good about because obviously you should not be cooling a room nobody is in. And the technician who looks concerned is simply someone who does not appreciate basic logic. Closing supply vents in a ducted HVAC system does not save energy. It increases static pressure throughout the entire duct system, forces the equipment to work harder, degrades system efficiency, and causes long-term physical damage to both the ductwork and the equipment. Residential duct systems are engineered using ACCA Manual D calculations that account for total system airflow in cubic feet per minute. The duct sizing assumes all registers are open. When you close vents, the blower still produces the same airflow volume. It now forces that air through fewer, smaller pathways, which increases static pressure throughout the system. Increased static pressure forces the blower motor to draw more amperage to maintain airflow, directly increasing energy consumption, the exact opposite of your intended outcome. Energy Star research confirms that residential duct systems already leak an average of 20 to 30% of conditioned air into unconditioned spaces like attics and crawl spaces. Closing vents increases pressure and accelerates this leakage, meaning more of your conditioned air ends up in the attic, not in your home. Closing return vents, which some homeowners confuse with supply vents, is particularly destructive, starving the air handler of intake air and creating conditions identical to a catastrophically clogged filter. The rooms you closed also exchange air with the rest of the home through gaps, door undercuts, and duct leakage, negating any thermal savings you imagined. The correct tool for room-by-room energy control is a zone system. Closing vents is like covering half the holes in a garden hose to use less water. The pump runs at full pressure. You have only changed where the damage occurs. 7. The HVAC system worked perfectly before the technician arrived. You are certain of this. And whatever the technician did during the last service visit is clearly responsible for the failure that emerged 2 weeks later, because the timing cannot be a coincidence, and coincidences are not something you believe in when you are also holding an invoice. HVAC components fail on their own timeline, governed by age, operating hours, electrical stress, and manufacturing tolerances, not by the scheduling calendar of the last maintenance visit. The most commonly failed components, capacitors, contactors, motors, heat exchangers, degrade gradually through thermal cycling, electrical arcing, and mechanical wear, and they reach their failure point at a specific moment in that degradation curve that has nothing to do with whether a technician was recently on site. Capacitors are the clearest example. A weakened capacitor can hold marginal readings on a multimeter during a maintenance check, pass the test, and then fail within days as operating temperatures rise seasonally. The technician did not weaken the capacitor, time and heat did. The "it worked before you came" logic also ignores the fact that most service calls are triggered because something is already not working. The technician is called to an already failing system. If they address one problem and a second failure surfaces 2 weeks later, those are two separate degradation timelines, not evidence of sabotage. Some components actually get stressed more during a diagnostic visit because the system is run at full load for the first time in a while. A contactor that was limping through partial operation may fail fully under that diagnostic load, like discovering a weak link only when you actually pull the chain. Blaming the technician for a part that failed after their visit is like blaming your doctor for your cold because you felt fine in the waiting room. 8. You have decided to run your HVAC fan on continuous on mode because you read somewhere, half an article, a forum thread, a confident stranger on the internet, that this improves air filtration and creates a healthier home environment, and you would like the technician to stop raising objections to your wellness research. Running the fan continuously on mode in a standard ducted system does circulate more air, and it also pulls warm, humid air through a non-cooling evaporator coil, re-evaporates condensation back into your home, raises indoor humidity measurably, and burns out blower motors faster than they were designed to wear. When a system runs normally in auto mode, the blower runs only during cooling cycles, and the evaporator coil actively removes moisture from the air as a byproduct of refrigeration. When the compressor shuts off and the fan continues in on mode, the moisture collected on the cold coil begins to re-evaporate into the airstream and back into your living space. In humid climates across the south and southeast, continuous fan operation can raise indoor relative humidity by 5 to 10 percentage points, directly undermining the dehumidification the cooling cycle just performed, and pushing humidity levels into ranges that promote mold growth and dust mite proliferation. PSC motors, the most common blower motor type in residential air handlers, are not designed for continuous 24-hour operation and experience dramatically shortened service lives under those conditions, with replacement costs running $300 to $600. The filtration argument has some merit, but is outweighed by the humidity and motor life costs for standard systems. The correctly engineered solution for continuous air filtration is a dedicated air purifier, not hijacking the blower of your central system. Running your HVAC fan continuously to improve air quality is like running your car's windshield wipers all day for better visibility. It does something. It also does several things you did not plan for. 9. The thermostat reads 72 degrees. You are standing in the kitchen in a light sweat, and you have concluded with complete confidence that the thermostat is lying, because you have a different thermometer on the other side of the house that reads 77, and you would like the technician to officially take your side in this dispute between you and an installed sensor. The thermostat is measuring the temperature at the thermostat. That reading is accurate for that location. The temperature on the other side of your home is a different measurement at a different location, and both can be simultaneously correct because they are measuring two different things in two different places. A thermostat is a point sensor. It reports what it measures immediately surrounding its sensor element. It is not reporting an average of your entire square footage. ACCA Manual T recommends thermostats be placed on interior walls, away from direct sunlight, heat-generating appliances, exterior doors, and supply registers, because all of these create false readings that throw off system operation. Temperature stratification in a residential space can produce genuine 5 to 8 degree variances between locations in the same room due to air movement patterns, solar gain through windows, and heat from appliances. And both readings can be accurate simultaneously. Digital thermostat accuracy is typically rated at plus or minus 1 to 2 degrees by manufacturers, a disclosed manufacturing tolerance, not a malfunction. A thermostat can also read falsely if positioned near a supply vent, near a return vent, or in a poorly insulated wall cavity that is influenced by outdoor temperatures. The actual diagnostic tool for validating thermostat accuracy is a calibrated digital thermometer placed at the same height and location as the thermostat sensor. Until that test is performed, the argument is entirely anecdotal. Telling your technician the thermostat is lying because your kitchen feels warmer is like telling a weather station it is wrong because your backyard is sunnier than the airport. 10. You have decided that the solution to every HVAC comfort problem is a larger unit, and the technician recommending a correctly sized system is clearly trying to undersell you. Because in every other area of life, more power means better performance, and there is no reason the laws of physics would work differently inside your home. An oversized HVAC system is one of the most common and most destructive errors in residential HVAC, and it produces the exact comfort problems you are trying to solve, while costing significantly more to purchase and operate. HVAC systems cool most efficiently during long, sustained operating cycles. An oversized system reaches the thermostat set point too quickly, shuts off, and then the space reheats and rehumidifies before the next cycle begins. The result is wide temperature swings and persistently high indoor humidity. The two primary drivers of comfort complaints. Dehumidification is a function of runtime. The longer the system runs per cycle, the more moisture it removes from the air. A short-cycling oversized unit may reach your target temperature while leaving indoor relative humidity at 65 to 70%, far above the 45 to 55% comfort target. Occupants feel clammy and uncomfortable despite the thermometer reading correctly. Compressors experience their highest mechanical and electrical stress at startup, so short cycling dramatically accelerates wear, compressing years of use into months, with compressor replacement running $1,500 to $2,800. Energy Star research has found that oversized equipment is installed in a significant percentage of American homes, contributing to unnecessary energy consumption and shortened equipment life. The ACA Manual J sizing calculation accounts for over 20 distinct variables and is the ANSI-approved engineering standard. Ignoring it and upsizing is not an upgrade. Demanding a bigger HVAC unit for better comfort is like demanding a bigger engine in a car with flat tires. More tonnage into a bad situation produces a more expensive bad situation. 11. Your summer utility bill arrived, you experienced a physical reaction to the total, and you have traced the cause directly back to the technician who serviced your system 2 months ago. Because something must have been miscalibrated, detuned, or deliberately altered to produce a number this large, and the timing points squarely at the person who was last inside the equipment. Residential energy bills are driven by dozens of variables that have nothing to do with service quality, and most of them are within your control. The U.S. Energy Information Administration reports that space heating and cooling account for roughly 46% of average home energy consumption. The remaining 54% is water heating, appliances, lighting, and electronics, none of which register when you are focused on blaming the HVAC system. Utility rates change seasonally and annually through mechanisms like time of use pricing, demand charges, and fuel adjustment clauses. A bill that increased 20% may reflect a 15% rate increase and a 5% consumption increase, with zero involvement from your technician. A 1-degree increase in average thermostat set point during cooling season corresponds to approximately 3 to 5% reduction in cooling energy consumption according to DOE modeling, meaning your behavior at the thermostat has more impact than any single maintenance procedure. Air infiltration and insulation degradation are primary drivers of excessive energy consumption. A home with deteriorated attic insulation or compromised window seals can see 20 to 30% excess energy use that no amount of HVAC servicing can offset because the problem is the building, not the equipment. Refrigerant charge, which is what most customers assume was tampered with, accounts for a bounded and measurable efficiency impact when deficient. The honest diagnostic path for high energy bills involves a utility bill audit and insulation inspection and a system efficiency evaluation. Blaming the HVAC tech for your energy bill is like blaming your mechanic for your gas bill. The car runs. The gas costs what it costs. 12. Several family members have mild congestion. You have traced the root cause to the air conditioning system with the confident precision of someone who has watched exactly one YouTube video, and your proposed solution is shutting the entire system down until everyone recovers. A plan you have presented to the technician as though it is obviously correct. Air conditioning systems do not cause illness. Poorly maintained air conditioning systems can distribute allergens or worsen pre-existing respiratory conditions, but the mechanism is the neglected maintenance, not the air conditioning itself, and turning it off in summer creates its own serious health risks that you have not accounted for. The common cold and influenza are caused by viruses, rhinovirus, various coronavirus strains, influenza A and B, that spread through direct human contact and respiratory droplets. An air conditioning system does not manufacture viruses, it cannot cause a cold. What HVAC systems can do when not maintained is recirculate allergens including pet dander, dust mite particles, and mold spores, which can worsen symptoms in people with pre-existing sensitivities. The solution is improved filtration, coil cleaning, and drain maintenance, not system shutdown. Evaporator coils that are not regularly cleaned can develop mold and microbial growth because they operate in a perpetually moist environment, and the EPA and ANADCA both document this risk and recommend periodic inspection and cleaning as a maintenance issue, not a design flaw. Air conditioning also reduces indoor humidity, which is broadly protective against mold growth and dust mite proliferation, both of which thrive in warm, humid conditions that your unair-conditioned summer home will provide in abundance. The CDC documents an average of over 1,300 heat-related deaths annually in the United States. Shutting off air conditioning during extreme heat to address a perceived respiratory complaint creates a measurable, documented, serious risk. Turning off the air conditioning because someone has a cold is like turning off the kitchen faucet because someone got food poisoning. 13. You found a self-service refrigerant can at the auto parts store, watched a 4-minute video, and you are genuinely curious why your technician is charging so much when you could apparently handle this yourself. Because both involve refrigerant, both involve hoses, and the visual similarity between your home, AC port, and the can nozzle seems promising. Automotive refrigerant cans use a completely different refrigerant than residential systems, connect to a different port configuration, and adding the wrong substance to your home system contaminates the refrigerant circuit in a way that requires a full recovery, flush, and recharge to correct. A process that runs $500 to $1,200 depending on system size. Residential central air conditioners built after 2010 use R410A, and newer systems are transitioning to R454B. Automotive systems use R134A or R-34YF. These are chemically distinct refrigerants operating at completely different pressures, and they are physically incompatible. Refrigerant service on residential HVAC systems requires EPA Section 608 certification under the Clean Air Act. It is illegal for uncertified individuals to purchase refrigerant in quantities above 2 pounds. The auto parts store cans are specifically formulated and packaged for automotive use and are explicitly not intended for HVAC systems. Proper residential refrigerant charging requires manifold gauge sets, a digital scale, and knowledge of the target subcooling and superheat values that vary by refrigerant type and system design. A color-coded gauge on a can provides none of this context. Overcharging refrigerant, brain. A primary risk of charging without measurement equipment causes liquid refrigerant to reach the compressor, a condition called liquid slugging that causes immediate, often catastrophic damage to compressor valves and pistons. Schrader valves on residential and automotive systems use the same core configuration, which creates the dangerous impression of compatibility. The similarity ends there. Using an auto parts can on your home AC is like using automotive brake fluid in your washing machine because both are fluid systems with reservoirs and hoses. 14. Annual HVAC maintenance is a scam. Things should be fixed when they break, and paying someone to look at a system that appears to be working is the HVAC industry's most elegant revenue extraction scheme. This is your position, and you would like the technician to acknowledge it before getting back in their truck. Annual HVAC maintenance has a documented return on investment through extended equipment life, reduced emergency repair frequency, maintained efficiency, and preserved manufacturer warranty coverage. Manufacturer warranties from Carrier, Trane, Lennox, Rheem, and other major brands routinely require annual professional maintenance as a condition of warranty validity. A compressor that fails at year 4 in a system with no documented maintenance history may be denied warranty coverage, turning a covered replacement into a $2,000 out-of-pocket expense. During a professional maintenance visit, technicians measure electrical amperage draw on motors and compressors, test capacitor microfarad ratings, measure refrigerant subcooling and superheat, inspect heat exchanger integrity on gas furnaces, clean evaporator and condenser coils, and verify thermostat calibration. These are measurements with quantifiable pass and fail thresholds, not theater. Dirty condenser coils alone, the most common finding on unmaintained systems, can reduce system efficiency by 5 to 30%, depending on severity, according to research published in ASHRAE journals. A coil cleaning restores efficiency and directly reduces your operating costs. The capacitor test is particularly high value. A capacitor testing at 70 to 80% of its rated microfarad value is statistically likely to fail within 1 to 2 seasons. Replacing it during a maintenance visit costs $80 to $150. Replacing it on the hottest day of the year after the compressor has been damaged by repeated hard starts against a failing capacitor costs dramatically more. Skipping annual HVAC maintenance to save money is the mechanical equivalent of skipping dental cleanings to save on dentist bills. Both strategies end in the same place: a much larger bill, much more pain, and a professional who has to fix what regular care would have prevented. 15. You need a new thermostat wire run from the air handler to the thermostat location. You have looked at the thin conductors, identified them as basically the same as old telephone wire, and you believe this is an afternoon project you can handle yourself. And the technician's labor quote for what amounts to running string through a wall seems like an obvious overcharge. Thermostat wiring carries live low-voltage electrical current, connects to both line voltage and low-voltage control components, must meet specific conductor gauge and configuration requirements, and incorrect installation can damage control boards that run $300 to $800 to replace. Standard thermostat wire is 18-gauge multi-conductor cable, available as 18.5, 18.7, or 18.8 depending on the number of conductors needed. While it is low voltage at 24 volts AC from the control transformer, it is a live circuit that must be connected to specific terminals on both the thermostat and the air handler. A shorted thermostat wire can blow the control transformer, which then requires replacement before the system will operate at all. Modern smart thermostats require a C wire, a continuous 24-volt common wire, for Wi-Fi and display functions. Homes wired with older 4-conductor cables lack this wire, requiring either a new cable run, an adapter kit, or creative rewiring that is not obvious to an untrained installer. Terminal labeling on HVAC control boards are C, Y, Y2, GO, W, W2, B, O, E, AUX, varies by manufacturer and system configuration, and two-stage systems, heat pumps, and dual fuel systems have wiring configurations that differ fundamentally from single-stage systems. Incorrect terminal assignment can cause the system to run heating during a cooling call, damage reversing valves on heat pumps, or prevent operation entirely. Telephone wire is 26 gauge, significantly thinner than the required 18 gauge, with higher electrical resistance per foot that can cause control board malfunctions on anything but the shortest runs. Thermostat wires being thin doesn't make them simple, the same way a surgical suture being thin doesn't make it something you do at home. 16. You walked outside, observed the condenser fan spinning, and heard the compressor running, and you have returned inside fully satisfied that the system is operational. Which makes the technician's suggestion that something may be wrong not just incorrect but genuinely offensive because you used your own eyes and ears and they reported back, running. The outdoor condenser unit operating does not confirm that the system is cooling effectively, that refrigerant charge is adequate, that the evaporator coil is functional, that airflow is sufficient, or that the system is doing anything beyond consuming electricity in a compromised state. A system can run continuously, condenser fan spinning, compressor humming, while severely undercharged on refrigerant. The refrigerant circuit is still cycling, but the heat exchange capacity is dramatically reduced. The outdoor unit provides no visual indication of refrigerant charge level whatsoever. A frozen evaporator coil encased in ice inside the air handler completely blocks airflow from being cooled while the outdoor unit continues operating normally. The condenser is doing its job rejecting heat, but there is no heat arriving from indoors because the evaporator is blocked. The system runs and achieves nothing. Compressors can operate while producing inadequate compression due to worn valve components, a condition only identifiable through pressure measurement, not by listening to the unit from outside. Condenser fans can also run independently of the compressor in some failure modes, particularly when a compressor capacitor has failed, because the fan motor and compressor motor use separate capacitors in most configurations. The correct verification of an HVAC system involves measuring supplier air temperature at the register, measuring return air temperature, calculating the delta T with a target of 14 to 22 degrees for cooling, and comparing to manufacturer specifications, not visual observation of the outdoor unit. Confirming your HVAC is working by watching the outdoor unit is like confirming your car's engine is healthy because it is running. 17. You purchased a new HVAC system with a 10-year parts warranty and have interpreted this as a comprehensive, all-inclusive policy that shields you from ever paying for anything HVAC related again for the next decade. And any mention of a service fee represents a contract violation that you are prepared to escalate aggressively. Parts warranties cover parts. They do not cover labor, refrigerant, diagnostic fees, maintenance, or the various components explicitly excluded from the warranty terms. Most customers have never read their warranty document and are describing a product that does not exist. Standard residential warranties from every major manufacturer explicitly cover defective parts only, not labor costs associated with replacement. Labor on a warranty compressor replacement can run $500 to $1,200 even when the part itself is covered at no charge. Warranty registration is required by most manufacturers within 30 to 60 days of installation to activate the full warranty period, and an unregistered system defaults to a shorter base coverage, often 5 years on parts instead of 10. Many homeowners never register and only discover this at the point of a warranty claim. Parts warranties also typically exclude consumable components including filters, fuses, and drain treatments, as well as components damaged by improper maintenance, electrical surges, unauthorized modifications, or acts of nature. Refrigerant is not a part. It is a consumable material, and no manufacturer warranty covers refrigerant costs associated with a leak repair. The diagnostic service call required to identify and document the failed component is also not covered under any manufacturer warranty, meaning the technician must be paid to diagnose and document before the warranty claim can even be submitted. Extended warranties purchased through the installer are entirely separate products with their own terms, exclusions, and deductibles. A parts-only HVAC warranty covering everything is like a car parts warranty covering your mechanic's time. The manufacturer made the component. They did not promise to send someone to your house to install a new one for free. 18. You have decided to run your HVAC fan on continuous on mode because you read somewhere that this creates better filtration. And now, 6 months into this experiment, your system has frozen twice. Your indoor humidity reads like a tropical greenhouse, and the blower motor has developed a sound your technician describes as end of life. But you feel confident the air quality is probably better. The fan-on myth keeps claiming victims specifically because it sounds reasonable. More air movement, more filtration passes, healthier home. What it actually produces in a standard ducted residential system without an electronically commutated motor is a sequence of consequences the half article never mentioned. PSC motors, the most common blower motor type installed in American homes, are not rated for continuous 24-hour operation, and degradation under those conditions is both measurable and predictable, with replacement cost running $300 to $600. Continuous fan operation in humid climates raises indoor relative humidity by 5 to 10 percentage points, because moisture collected on the cold evaporator coil during cooling cycles re-evaporates into the airstream the moment the compressor stops and the fan continues, undoing the dehumidification work of the cooling cycle in real time. In ASHRAE climate zones 1 through 3, covering the south and southeast, this is not a marginal concern. It is a direct path to the indoor humidity range where mold growth, dust mite proliferation, and persistent discomfort become your new normal. The correctly engineered solution for continuous filtration benefit without the humidity and motor life penalties is an electronically commutated motor, a premium component found in higher-end systems, or a dedicated standalone air purifier. Running your standard air handler fan continuously to improve air quality is like running your car's windshield wipers around the clock for better visibility. It technically does something. It also does several other things you did not budget for, and eventually it does nothing because the motor's gone. 19. The thermostat is in a bad spot. That is your diagnosis, delivered with the certainty of someone who has spent 45 minutes on a home improvement forum. And moving it to the upstairs hallway will solve the short cycling problem, the humidity problem, and probably several issues you have not identified yet. Thermostat location can cause short cycling in one specific, well-defined scenario. The thermostat is mounted directly in the path of supply. Air from a nearby register, the cooled air satisfies the sensor before the occupied space is adequately conditioned, and the system shuts off prematurely. This is a real installation problem, but it typically manifests from the initial installation, not suddenly after years of normal operation in a system that previously ran fine. Short cycling has a differential diagnosis with multiple distinct root causes, each requiring a different corrective action, and thermostat location is rarely the primary cause in a system that changed behavior after working correctly for years. Oversized equipment is the most common cause of persistent short cycling. An oversized system satisfies the thermostat quickly, regardless of where the thermostat is located, because the equipment has excess cooling capacity relative to the actual load. Moving the thermostat to a location that satisfies more slowly simply extends cycle time without correcting the fundamental mismatch between equipment capacity and building load. A capacitor failure causing the compressor to struggle and trip its thermal overload, a high head pressure safety switch tripping because the condenser coil is fouled, and a low pressure switch tripping because the refrigerant charge is low. All of these produce short cycling symptoms that relocation will not touch. Moving the thermostat is one legitimate item on a multi-point differential diagnosis, not a universal solution you arrived at through intuition. Moving the thermostat to stop short cycling is the HVAC equivalent of moving the fuel gauge in your car because it reads empty too quickly. Sometimes the gauge placement is the problem. More often, the car needs fuel. 20. You have an oversized system short cycling in your home, and your proposed solution is to add refrigerant. Because refrigerant is the variable you have heard the most about, the system is clearly doing something wrong, and the two facts feel connected in a way that seems logical if you do not examine it too carefully. Short cycling has multiple distinct causes, and diagnosing refrigerant as the culprit without measurement instruments is not diagnosis. It is guessing, and it is the kind of guessing that makes a marginal situation significantly more expensive. An oversized system short cycles by design, reaching the thermostat set point before a full cycle can complete because it has excess cooling capacity relative to the building load. Adding refrigerant to an oversized system increases the already excessive cooling capacity and makes the short cycling worse, not better. A frozen evaporator coil causes the low pressure safety switch to shut the compressor off as suction pressure drops below its threshold. The system then sits idle while the coil partially thaws, restarts, freezes again, and repeats in a pattern that looks like short cycling but is actually a freeze-thaw cycle driven by airflow restriction, not refrigerant. A poorly calibrated thermostat can trigger premature cycle termination, mimicking short cycling without any equipment fault at all. Actual low refrigerant does cause low suction pressure, which can trip the low pressure safety switch and produce short cycles. But this diagnosis requires measuring suction pressure with a manifold gauge set, a measurement that definitively indicates refrigerant status. The difference between this and what you are doing is the instrument in the technician's hand. Rapid short cycling is also mechanically harmful, regardless of cause, subjecting the compressor to repeated startup loads without adequate refrigerant and oil circulation. Deciding your short cycling system needs refrigerant is like deciding your stalling engine needs premium fuel. Maybe. or maybe it is 10 other things. The instruments decide. 21. Boiling water from a questionable source in the wilderness makes it completely safe to drink, and the technician who is servicing your whole house water filtration system has no business questioning your outdoor survival philosophy. Though this myth operates on the same fundamental logic error that you also apply to your HVAC system, which is that one action neutralizes all possible threats simultaneously. This item is for the version of you that believes a single intervention solves every problem in a complex system. In water, boiling eliminates biological threats, bacteria and parasites, while doing absolutely nothing to remove chemicals, heavy metals, or industrial contaminants. The same logic failure shows up constantly in HVAC. One action is assumed to solve everything, the system is treated as simpler than it is, and the diagnosis stops the moment a plausible sounding answer appears. Your home's air system has biological threats, chemical concerns, particulate matter, humidity variables, pressure dynamics, and electrical components. And the fix for one does not address the others. Changing the filter fixes restricted airflow, but not a refrigerant leak. Cleaning the coil fixes heat transfer efficiency, but not a failing capacitor. Adding refrigerant fixes low charge, but not a fouled condenser. Each problem in your HVAC system has a specific cause, a specific diagnostic measurement, and a specific corrective action. And the assumption that one service addresses all of them is the reason callbacks exist. A technician who checks one variable and leaves is not finished. A homeowner who watches one variable and declares the system healthy is not diagnosing. Complex systems fail at specific points for specific reasons, and the resolution of one failure does not inoculate against the next. Boiling treats the biology, the chemicals are still there. Your HVAC system works the same way. 22. HVAC companies charge more in summer because they are greedy. The pricing should be the same year-round, and the premium you were quoted for a Saturday afternoon service call in the middle of July is pure opportunism dressed up as a scheduling policy. And you would like the technician to acknowledge this before they begin. Summer. HVAC pricing reflects real documentable market forces that have nothing to do with greed and everything to do with the economics of dispatching a licensed, insured, EPA-certified technician with a fully stocked service vehicle during the highest demand period of the operational year. A significant percentage of annual service calls occur during June through August, when system failures are most likely and most impactful. During this period, companies operate at maximum technician capacity, requiring overtime labor, weekend scheduling, and emergency dispatch, all of which carry legitimate cost premiums that reflect real payroll expenses. Parts pricing and availability during peak season reflects supply chain realities. Capacitors, contactors, and refrigerant are subject to seasonal demand increases that affect wholesale pricing. This is standard supply and demand economics, operating exactly as described in every introductory economics course. The concept of emergency service pricing is not unique to HVAC. Plumbers, electricians, locksmiths, and tow truck operators all charge premiums for after-hours, weekend, and holiday calls because a technician available on a Saturday night during a heat wave is providing a premium service at a premium cost. Companies that offer flat year-round pricing average it, charging more during off-season to subsidize peak season rates. Neither model is dishonest, both reflect real cost structures. Preventive maintenance contracts are the industry standard mechanism for securing preferential pricing and priority scheduling year-round, and they are available to you in October, November, March, and April, when the technician is not already booked solid. Complaining about higher HVAC rates in July is like complaining that an umbrella costs more during a rainstorm. The price reflects the moment. 23. Your system is 22 years old. It still turns on when asked. It produces some degree of conditioned air, and any suggestion of replacement is transparently an upsell. Because working means operational, and operational means there is no problem, and there is definitely no problem. And you would appreciate it if the technician would stop implying otherwise. A 22-year-old system that turns on and moves air may be operating at 40 to 60% of its original efficiency, consuming 30 to 50% more electricity than a modern replacement containing a refrigerant that was banned from production in 2020, and representing a parts supply chain that is increasingly difficult and expensive to access. Typical residential systems from the late 1990s and early 2000s were rated at 8 to 10 SEER. Current federal minimum efficiency standards require 13.4 SEER2 in northern states and 14.3 SEER2 in southern states, with modern premium units reaching 20 to 26 SEER2. Efficiency also degrades over time. A system rated at 10 SEER new may be operating at effectively 6 to 7 SEER after 2 decades of coil fouling, refrigerant loss, and worn compressor valves. R22 refrigerant, used in systems built before 2010, was banned from U.S. production and import as of January 1, 2020 under the EPA's phase-out schedule. Available R22 now comes only from reclamation and recovery, and prices have risen dramatically. A refrigerant leak in your R22 system has no long-term solution except replacement. ASHRAE, the Air Conditioning, Heating, and Refrigeration Institute, and Home Inspection Standards all publish equipment service life estimates of 15 to 20 years for central air conditioners. Your system is past every published standard by 2 to 7 years. Keeping a 22-year-old HVAC system because it turns on is the mechanical equivalent of keeping a 22-year-old car because it starts. Starting and performing efficiently are two very different standards. 24, the technician recommended replacing your aging equipment, and you have decided this recommendation exists entirely because of sales commission. Because the technician's financial interest is, in your view, the only possible reason a replacement recommendation could exist, and the diagnosis itself is secondary to the motive you have assigned. Commission structures in HVAC exist, but they do not fabricate failing equipment, manufacture refrigerant leaks, or invent the electrical readings on a calibrated multimeter. Most service-only technicians, the ones dispatched to diagnostic and repair calls, are paid flat hourly wages or flat rate per call compensation, not commission on equipment sales. Their financial interest is in completing service calls efficiently, not in constructing elaborate replacement justifications for appliances they are standing next to with instruments in their hands. When replacement is recommended during a service call, it is typically because the technician has measured something specific: a compressor drawing locked rotor amperage instead of rated load amperage, a heat exchanger with a confirmed crack identified by combustion gas measurement, a refrigerant charge that cannot be maintained without a repair that costs more than the system's remaining useful value. The industry rule of thumb: if a repair cost exceeds 50% of the system's replacement cost and the system is over 10 years old, replacement is the economically rational choice, is basic present value analysis, not a commission formula. Technicians who fabricate problems risk their EPA Section 608 certification and contractor's license, both of which represent far more long-term value than any individual commission. Requesting a second opinion from an independent company is a completely legitimate consumer protection step, and a technician confident in their diagnosis will welcome it rather than resist it. Assuming replacement recommendations are always commissions-driven is like assuming your doctor only orders tests to bill your insurance. The diagnosis either matches the measurements or it doesn't. Ask for the data. 25. A fan blowing over a bucket of ice is basically air conditioning. You have one running in the bedroom right now, and you call to say there is no particular rush because you have the situation handled and can wait a few days for the technician to come by when they have an opening. A fan blowing over ice lowers air temperature by a small margin for a short time until the ice melts, after which you have a fan blowing over a container of warm water. It does not dehumidify, cannot maintain temperature, cannot condition an entire room, and is not comparable to air conditioning by any measurable standard. A 2-ton central air conditioning system moves 24,000 BTUs of heat per hour out of a home, continuously for as many hours as needed. A standard bag of ice contains roughly 9,750 BTUs of total cooling capacity. Your system delivers more than twice a full bag of ice's entire cooling capacity every single hour without replacement. Air conditioning also removes moisture from the air as a core function of the refrigeration cycle. A fan blowing over ice does not dehumidify. As the ice melts, it contributes water vapor to the air, potentially raising indoor humidity and making the same temperature feel warmer. The evaporative cooling effect from a fan over ice produces a measurable but modest temperature drop in the immediate airstream, perhaps 3 to 5 degrees at the fan face, that dissipates rapidly across the room and disappears entirely once the ice is gone, which in an 85-degree room takes 2 to 3 hours. The CDC and state health departments specifically distinguish between cooling measures like fans and actual air-conditioned spaces in their heat emergency guidance, because the difference in heat stress mitigation is significant. Ice in front of a fan is to air conditioning what a candle is to a light bulb. The ice is gone in 3 hours, the heat is not. 26. You installed a smart thermostat, you expected your energy bill to drop by half. 2 months have passed, the bill has not meaningfully changed, and the product clearly does not work or was installed incorrectly, and you would like the technician to explain what went wrong during the installation. Smart thermostats optimize scheduling and setback strategies. They cannot make a low-efficiency system efficient, cannot compensate for duct losses, cannot address failures in the building envelope, and deliver energy savings proportional to how badly the previous thermostat was being mismanaged, which varies enormously between households and is entirely outside the device's control. The Department of Energy's published estimate for programmable thermostat savings is 10% per year on heating and cooling costs when setback schedules are actually used. And this figure applies to any properly used programmable thermostat, not specifically to smart devices. A household that was already manually adjusting their thermostat with reasonable discipline sees minimal additional savings from automation because there was nothing left to optimize. Google Nest's internal research found average energy savings of 10 to 15% for heating and 15% for cooling in homes where their devices were properly installed and used. Averages across diverse usage patterns, not a guarantee for your specific home with your specific system in your specific climate. A smart thermostat cannot improve the efficiency of the HVAC equipment it controls. A 10-SEER system controlled by a smart thermostat is still a 10-SEER system. The intelligence of the control device does not alter the physics of the equipment. The largest energy savings available to most homeowners come from equipment efficiency, duct sealing, and building insulation. Smart thermostats are the last 10%, not the first. Expecting a smart thermostat to cut your bill in half is like expecting a better steering wheel to improve your fuel economy. It helps you drive smarter. It does not change what is under the hood. 27. There is water sitting in the secondary condensate drain pan beneath your air handler. You have noticed it. You have concluded this is normal because water is involved in air conditioning somehow, and you have decided to mention it to the technician only as an afterthought while describing 3 other complaints you consider more pressing. The secondary condensate drain pan is an emergency overflow device. Water sitting in it means the primary condensate drain is blocked and the system has been draining into the overflow pan, which is one step from water damage to your ceiling, attic, or the floor structure beneath the air handler, depending on where the unit is installed. All air conditioning systems produce condensate, liquid water, as a byproduct of cooling and dehumidifying indoor air. A residential system in a humid climate produces 5 to 20 gallons of condensate per day. This drains through the primary condensate drain line to a floor drain, utility sink, or exterior discharge point. The primary drain, typically PVC pipe, is susceptible to algae, mold, and debris accumulation that eventually creates a blockage. When the primary drain is blocked, water backs up until it overflows into the secondary pan, which is where you are now. The secondary pan has one purpose: to contain water long enough for you to notice before damage occurs. Some secondary pans include a float switch that shuts the system off when water accumulates, a safety device specifically designed to prevent the damage you are currently one plumbing backup away from. A clogged primary drain is one of the most common and fully preventable causes of HVAC-related water damage in residential homes, with remediation costs ranging from $500 to several thousand depending on extent. Water in your secondary pan is not a routine feature, it is an alarm. The HVAC system has been trying to tell you something for however long that pan has had water in it. 28. You had a UV germicidal light installed in your HVAC system. You have described the results to your neighbors as a hospital-grade air purification, and when the technician arrives for the annual check, you would like them to confirm that your home's air quality is now equivalent to a surgical suite, because that is what the brochure implied and you took it literally. UV lights installed in HVAC systems provide real but bounded benefits, primarily mold and bacterial control on the evaporator coil surface. They are not capable of sterilizing the airstream to clinical standards, do not neutralize all pathogens, and the hospital-grade comparison is a marketing analogy, not a technical specification backed by any measurement of your indoor air. For coil sterilization, UVC light is well documented as effective. Studies published in Applied and Environmental Microbiology have demonstrated meaningful reductions in microbial populations on coil surfaces with continuous UVC exposure. This is legitimate and worth having. For airstream sterilization, efficacy is a function of exposure time and intensity. At typical residential airflow rates of 400 to 2,000 cubic feet per minute, air passes the UV lamp in milliseconds. Hospital UV sterilization systems use much higher intensities, longer exposure times, and separate treatment chambers, not inline duct installation. The comparison is structurally misleading. True hospital-grade air handling requires HEPA filtration that removes 99.97% of particles 0.3 microns and larger, a filtration level that standard residential duct systems cannot accommodate due to airflow resistance. UVC bulbs also require annual replacement to maintain effectiveness because UV output degrades over time while the bulb continues producing visible light. An old, unreplaced UV bulb may produce virtually no germicidal output while appearing fully operational. The EPA recognizes UV germicidal irradiation as a supplemental control measure, not a primary air quality solution. A UV light in your HVAC is a useful tool. Calling it hospital grade is like calling a home smoke detector clinical grade monitoring. 29. Your system is 7 years old, it has failed, and you are not merely inconvenienced, you are philosophically offended. Because equipment under 10 years old should not fail, this failure represents a fundamental breach of the natural order, and someone connected to the installation, the manufacturer, or the service history owes you an explanation that does not involve you paying anything. HVAC system age is one factor in reliability. Operating hours, installation quality, maintenance history, electrical environment, and component manufacturing variability are equally determinative, and a 7-year-old system can fail for entirely normal reasons that have no relationship to its calendar age. The most commonly failed component in residential HVAC, the run capacitor, has a rated service life of approximately 5 to 10 years under normal operating conditions. A 7-year-old system with original capacitors is well within the statistically expected window for first capacitor failure. This is not a defect. It is a consumable component reaching the end of its designed service life. Installation quality has a profound impact on component longevity. An undersized system running long cycles, an oversized system short cycling, improperly charged refrigerant from day one, or a blower motor operating against high static pressure due to undersized ductwork all create elevated mechanical stress that accelerates wear relative to calendar age. Electrical environment matters significantly as well. Homes with frequent power fluctuations, voltage sags, or inadequate wire gauge to the outdoor unit experience premature capacitor, contactor, and control board failures regardless of system age. Manufacturing variability also exists in all mass-produced equipment. Statistical component failure distributions follow known reliability curves in engineering, meaning some percentage of any component population will fail early as a natural result of manufacturing tolerances. Manufacturer warranties exist because manufacturers know components fail within the warranty window at a predictable rate. They are actuarially priced, not optimistic guesses. Expecting a 7-year-old system to be failure-proof is like expecting a 7-year-old car to never need anything beyond fuel. 30, the technician came, the system ran, the technician left, the problem returned the next day, and this sequence of events constitutes incontrovertible proof that the repair was ineffective, the technician was incompetent, or the part was defective, and you would like a full refund and a different technician sent immediately. A repaired component that fails again quickly may indicate a secondary underlying cause that destroyed the replacement part, or a different component failed independently, and neither outcome means the original repair was performed incorrectly. Capacitors are the clearest illustration of this pattern. A failed run capacitor is replaced, the system runs correctly, and the new capacitor fails within a week. The correct diagnosis in this scenario is not a bad capacitor. It is that the compressor or motor is drawing above rated amperage due to worn bearings or inadequate refrigerant charge, and that elevated current is destroying capacitors regardless of how many times they are replaced. The capacitor was the symptom. The current draw is the cause. Electrical components in HVAC systems are interconnected in cause and effect chains. A failed contactor can cause voltage irregularities that damage the control board, and a damaged control board can cause improper sequencing that stresses the compressor. Repairing one component without evaluating the health of adjacent components leaves the root cause potentially unaddressed and the replacement part exposed to the same damaging condition. Intermittent failure modes, expansion valves, certain pressure switches, can work normally during a service call and fail under specific pressure and temperature conditions that only appear later under particular operating conditions. Customers frequently interpret two separate component failures as one failed repair, when they are actually two distinct failures occurring in temporal proximity. A repair that holds for 24 hours before something else fails is not necessarily a bad repair. Sometimes you fix a flat tire and the engine quits on the way home. Both things were true at the same time. 31. You hold your hand over a supply register 30 seconds after the system starts, feel room temperature air, and call the technician to report that the system is not cooling. Because if it were working, the air coming out would already be cold, and the air coming out is not cold, and therefore something is wrong, and you need someone here today. There is a normal, physics-governed delay between system startup and cold air delivery at registers, typically 2 to 5 minutes. And the air that arrives first is simply the air that was already sitting in the ductwork at ambient temperature while the system was off. At startup, the refrigerant circuit requires time to reach steady-state operating pressures. The compressor begins circulating refrigerant, suction pressure drops, and the evaporator coil begins to cool. This process, from compressor activation to full evaporator coil cooling effectiveness, takes approximately 2 to 5 minutes depending on outdoor temperature, refrigerant type, and system size. The air inside the ductwork at the moment of startup is at whatever temperature the ductwork was sitting at during the off cycle, which in an attic-mounted system in summer can be quite warm. This air, the contents of the duct at the moment the blower starts, is the first air to reach the registers. The supply air temperature during this initial period accurately reflects the duct air temperature, not the system's cooling capacity. The delta T measurement the technicians use to evaluate cooling performance, the difference between return air temperature and supply air temperature, should be taken after the system has run for a minimum of 15 to 20 minutes at steady state, after the refrigerant circuit has stabilized and the duct air has been replaced by conditioned air. Holding your hand over a register 30 seconds after startup and declaring the system broken is like turning on your shower, touching the water immediately, and filing a complaint with the water heater manufacturer. 32. You upgraded from a standard 1-inch MERV 8 filter to a thick MERV 13 filter because better filtration is obviously better. You are proud of this decision, and the technician's expression of concern when they opened the filter compartment is unwelcome interference with what you correctly identified as an improvement. Installing a high MERV filter in a system not engineered to accommodate it creates significant airflow restriction, increases static pressure, reduces airflow across the evaporator coil, and produces exactly the same symptoms as a catastrophically clogged filter: frozen coils, reduced capacity, and compressor stress. MERV ratings measure a filter's ability to capture particles of various sizes. Higher ratings capture finer particles using denser filter media that resists airflow more aggressively. The filtration benefit and the airflow penalty both increase proportionally with MERV rating, and your air handler was designed to operate within a specific external static pressure range, typically 0.1 to 0.5 inches of water column. A high MERV filter can add 0.1 to 0.3 inches of additional static pressure resistance, which may push the system beyond its design range, reducing airflow and blower motor efficiency simultaneously. A MERV 13 filter with high phase velocity also loads with dust and debris significantly faster than a lower MERV filter, meaning the restriction worsens more rapidly and requires more frequent replacement to avoid the damage it was selected to prevent. 4-inch thick media filters are designed for use in specific filter cabinets sized to maintain acceptable phase velocity for that media density. They are not interchangeable with 1-inch filter slots by simply pressing them into a narrower frame. ASHRAE's guidance on filter selection explicitly notes that filter choice must be validated against system airflow capacity, not selected, independently based on a MERV rating. The correct path is identifying the highest MERV rating your specific system can handle without exceeding its static pressure design range. Installing the highest number you can find is like putting racing tires on a family sedan for better performance. 33. Every fall, you carefully cover your outdoor condenser unit with a tarp or a custom cover to protect it from winter weather. You consider this responsible home ownership, and the technician suggesting you remove it is clearly someone who does not appreciate proactive property maintenance. Fully covering an outdoor condenser unit creates a warm, dark, enclosed, protected habitat that small animals, mice, squirrels, chipmunks readily colonize over winter. They nest in the components, and they chew wiring insulation, capacitor leads, contactor wiring, and any other accessible material inside the cabinet. Rodent damage to HVAC wiring is one of the most consistent spring startup failure modes in regions where full covers are popular, and the damage is both extensive and entirely preventable. Residential outdoor condenser units are manufactured and tested to UL and AHRI standards for outdoor exposure. The cabinet, electrical components, and coil are all designed and rated for weather, rain, snow, ice, and UV radiation. Because outdoor exposure is the design condition, not an oversight. Ice forming on a condenser unit is not damaging to the equipment. Condenser coil aluminum fins are designed for freeze-thaw cycles. The ice naturally melts when temperatures rise. This is not a service issue. The one legitimate winter protection concern is debris, leaves, seeds, cottonwood fluff, accumulating inside the unit. The correct solution is a partial top cover that blocks falling debris while leaving all four sides open for ventilation, which does not create the enclosed habitat that motivates rodent colonization. Heat pumps must never be fully covered regardless of season, since they operate in heating mode through winter and require outdoor air exchange for that operation. The single valid additional concern is a drip guard if the unit sits under a roof edge where ice slides could impact the coil directly. Covering your outdoor AC unit for winter is practically an engraved invitation for rodents. You built them a winter cabin with a catered wiring buffet. 34. You turned off the HVAC system at the breaker before leaving for a 2-week summer vacation. You are proud of the energy-saving discipline this represents, and you mentioned it to the technician as context for why the system has been off for 15 days in August, in a region that regularly sees 90-degree temperatures and 80% relative humidity. In humid climates, shutting off the HVAC system for extended periods allows indoor humidity to rise to levels that actively promote mold growth on surfaces, in duct systems, and on interior furnishings. A remediation problem that can cost dramatically more than 2 weeks of energy savings. In ASHRAE climate zones 1 through 3, covering Florida, the Gulf Coast, the Southeast, and portions of the Mid-Atlantic, indoor relative humidity in an unoccupied, unconditioned home can reach 80 to 95% within days during summer. Mold growth on building materials begins at sustained relative humidity above 60 to 65%. 2 weeks at that humidity range in a warm home creates conditions sufficient for visible mold growth on walls, furniture, clothing, and HVAC components, particularly the evaporator coil and any duct liner. Mold remediation in residential settings typically costs $500 to $6,000 depending on extent and affected materials. The responsible vacation energy strategy is a high setback, not a complete shutdown. The DOE recommends setting cooling to 85 to 88 degrees during extended absences, allowing the system to cycle occasionally and control humidity. Complete system shutdown also means the condensate drain is not being exercised for 15 days in a warm environment, and restarting the system after a full-off period often pushes a mold or algae plug through the drain, which overflows into the secondary pan and causes the water damage you shut the system off to avoid. Turning off your HVAC before a 2-week summer vacation in a humid climate is the energy-saving strategy that pays for itself in mold remediation. You saved $80. The mold bill is $3,000. 35. Your system is producing cool air from the vents. The temperature at the register is noticeably below room temperature, and this definitively proves the refrigerant charge is correct. Because cold air means refrigerant working means the charge is right, and the technician connecting gauges to the service ports is wasting time confirming something you have already confirmed with your hand. A system can produce cool air, measurably below ambient temperature, while being significantly overcharged or undercharged on refrigerant. Both conditions reduce efficiency, stress the compressor, and cause progressive damage that is invisible to anyone standing at the register. Refrigerant charge is evaluated through 2 primary measurements: subcooling on the high side liquid line and superheat on the low side suction line. Both require manifold gauges and temperature clamps. Neither can be inferred from the air temperature at the register. An undercharged system cools, but inefficiently. Suction pressure drops, suction line temperature falls, and the compressor operates with inadequate mass flow and elevated compression ratio. The system moves cooled air while running under conditions that cause long-term compressor damage through inadequate lubrication and elevated discharge temperatures. An overcharged system also cools, but with elevated head pressure and elevated compressor discharge temperature. and liquid refrigerant can reach the compressor in overcharged conditions, causing immediate mechanical damage to valve assemblies and pistons. The delta T measurement provides a rough efficiency indicator but cannot validate refrigerant charge. The same supply air temperature can result from low refrigerant, restricted airflow, a dirty coil, or duct leakage, and each cause requires a different corrective action. Technicians use manufacturer-published charging charts that specify target subcooling and superheat values at specific ambient conditions, a process that requires instruments and has no shortcut. Deciding your refrigerant charge is correct because the air is cool is like deciding your tire pressure is correct because the car moves. One requires an instrument, the other is just watching something happen. 36. You have moved the thermostat upstairs because heat rises, and the upstairs location gives you a more accurate reading of the home's average temperature, which means the system will now control your indoor environment more precisely. And you would like the technician to validate this before you patch the wall where the old thermostat was. Heat rising is real. A thermostat installed where occupants primarily live, sleep, and spend time is the correct application of that fact. Placing the thermostat in the naturally warmer upper floor causes the system to cool more aggressively to satisfy the upstairs sensor, which overcools the main living areas where your family actually spends 80% of their waking hours. ACCA Manual T, the industry standard for thermostat placement, specifies interior walls, away from supply registers, return grills, exterior doors, windows with direct solar gain, and heat-generating appliances. Floor level is not the primary placement criterion, the occupied zone is. In a two-story home with a single-zone system, the correct response to temperature differential between floors is airflow balancing through register damper adjustment, a booster fan in specific duct runs, or a properly designed zoned system, not thermostat relocation to the warmer zone, which simply moves the control point to the area that is hardest to condition and most likely to call for excessive cooling. Upstairs, thermostat placement in summer also causes the compressor to run longer cycles because the upper floor receives more solar radiation through the roof and is structurally more difficult to cool. The main floor may reach uncomfortably cold temperatures before the thermostat upstairs is satisfied. The average American home has its thermostat on the main floor by design, based on decades of real-world comfort data compiled by manufacturers and ACCA, not arbitrary tradition. Putting the thermostat upstairs because heat rises is like moving the smoke detector to the attic because smoke also rises. You applied a correct physics fact to entirely the wrong problem. 37. Your standard central air conditioning system should be maintaining comfortable humidity levels year-round without any additional equipment, and the fact that your skin is cracking, your floors are warping, and static electricity is following you room to room in January is clearly the system's fault. Because you paid for climate control, and humidity is part of the climate. Standard central air conditioning systems are designed to remove humidity during cooling season as a byproduct of refrigeration. They are not designed to add humidity during heating season, and a gas furnace or heat pump running in heating mode actively dries indoor air rather than maintaining it. During cooling season, moisture condenses on the cold evaporator coil and drains away. But this dehumidification is not independently controlled, and a dedicated whole home dehumidifier is the only way to control humidity separately from the cooling cycle. During heating season, furnaces and electric resistance heat strips add zero moisture to the air. They raise air temperature, which reduces relative humidity because warmer air can hold more moisture, but the absolute moisture content of the air remains unchanged. Indoor relative humidity in a heated home in winter routinely drops to 15 to 25% without supplemental humidification. ASHRAE, standard 55, identifies the acceptable indoor humidity range as 30 to 60% relative humidity for year-round comfort and health. Below 30%, occupants experience dry mucous membranes, increased susceptibility to respiratory viruses, static electricity discharge, and wood shrinkage in furniture and flooring. Whole home humidifiers, bypass, fan-powered, or steam types, integrate with the furnace and ductwork to deliver controlled moisture during heating season. They are separate products requiring separate installation and annual maintenance. They are not features that were accidentally left out of your system. Expecting a standard HVAC system to control humidity in both directions is like expecting your car's heater to also function as an air freshener because both affect the interior environment. Related systems, not the same product. 38. Your system is malfunctioning. Your first response was to turn it off and back on at the thermostat. Your second response was to turn it off and back on at the breaker, and you are now presenting this power cycling history to the technician as a record of diagnostic effort that should be factored into whatever you are about to be charged. Power cycling in HVAC system addresses exactly one category of failure: a software-level lockout or nuisance trip on a digital control board where a memory state reset clears the fault. It does not fix refrigerant leaks, failed capacitors, burned contactors, frozen coils, clogged drains, cracked heat exchangers, or any physical or mechanical failure mode that exists at the molecular or structural level. Modern HVAC control boards include fault lockout logic. When the system detects a safety condition such as high pressure, low pressure, flame rollout, or repeated ignition failure, it enters a lockout state that prevents operation. Cycling power resets this lockout, which is the one scenario where power cycling has both diagnostic and corrective value. And it is also a clue that a safety switch tripped for a reason, which means the underlying cause that triggered the lockout is still present and waiting to trigger it again. Resetting a safety lockout without identifying the underlying cause means the system will run until it detects the same safety condition, locks out again, and you call again. Repeated power cycling of a system with a hard starting compressor forces current through the compressor windings at locked rotor amperage, typically 5 to 7 times the normal running amperage, overheating motor windings and accelerating insulation breakdown in a way that turns a marginal compressor into a failed one. HVAC mechanical components do not have software states. A burned contact is burned regardless of what the breaker position was for the past 40 minutes. Power cycling your HVAC to fix a mechanical failure is like restarting your car to fix a flat tire. The reboot completed. The flat is still flat. 39. You would like the technician to tell you what is wrong with the system just by looking at it, because experienced mechanics can diagnose engines by sound, and this should work the same way, and the instruments being connected to service ports feel like stalling before the real answer is delivered. HVAC diagnostics require instrumented measurement because every variable that determines system health, refrigerant pressure, electrical amperage, airflow volume, temperature differential, is invisible to the naked eye and cannot be accurately estimated by observation, sound, or professional intuition applied without data. Refrigerant pressure is the central diagnostic variable in cooling system evaluation, and it cannot be estimated visually under any circumstances. The system looks identical whether it is properly charged, 20% undercharged, or 20% overcharged. The only way to know is to connect a calibrated manifold gauge set to the service ports and read suction and discharge pressures against manufacturer specifications. Electrical amperage draw, critical for assessing compressor and motor health, requires a clamp meter placed around the conductor. A compressor drawing 15 amps on a 12 amp rated unit is failing. A compressor drawing 8 amps on the same unit may have weak valves. Neither condition produces a visible or audible signature in its early stages. Capacitor health is measured in microfarads using a multimeter in capacitor mode. A capacitor at 80% of rated value looks physically identical to one at 100% and one at 30%. All three are cylindrical metal cans of the same size. Airflow measurement requires either a calibrated flow hood, a velocity meter, or a static pressure calculation. Without these instruments, airflow adequacy is unknowable. The experienced mechanic diagnosing by sound is using trained auditory pattern recognition built from thousands of operating hours. A real skill for identifying gross failures, not a substitute for pressure, electrical, and airflow measurement. Asking your HVAC technician to diagnose the system without instruments is like asking a doctor to assess your blood pressure by looking at you. 40. Your system smells musty when it runs. You have connected musty smell to something being wrong with the system. You have connected something being wrong to refrigerant because refrigerant is the HVAC variable, you know by name, and you would like the technician to recharge the system and see if that takes care of the odor. A musty smell from your HVAC system is caused by microbial growth, mold, mildew, and bacteria, on the evaporator coil, in the condensate drain pan, in the ductwork, or on contaminated filter media. Refrigerant is odorless. R410A and R22 are both essentially odorless under normal operating conditions. The chemical composition of modern refrigerants does not include compounds that produce musty, earthy, or organic odors. A musty smell is biological in origin, not chemical, and refrigerant charge level has no relationship to it whatsoever. The evaporator coil operates at temperatures between 35 and 50 degrees Fahrenheit while actively cooling, making it a cold, consistently moist surface that accumulates condensate during every cooling cycle and provides an environment well suited to mold and mildew growth. The condensate drain pan, when partially clogged with organic debris, maintains standing water beneath the coil that accumulates algae, bacteria, and mold, all of which produce volatile organic compounds distributed through the airstream as musty odors with every system cycle. Duct liner, the fiberglass or foam lining inside some ductwork, is porous, absorbs moisture, and once contaminated with mold is effectively impossible to clean without replacement. The correct remediation involves evaporator coil cleaning with an EPA-registered coil cleaner, drain pan cleaning and treatment with algicide tablets, and drain line flushing. Adding refrigerant to a musty system changes nothing about the biological conditions producing the odor. Calling for a refrigerant charge because your system smells musty is like putting premium fuel in your car because the interior smells like mildew. The refrigerant is fine. The smell is coming from a completely different department. 41. You have decided the outdoor condenser does not need cleaning because it rains regularly and rain washes it. A theory that is logical, free, and wrong. And you have now presented this to the technician as the reason the unit has not been touched in 6 years. Rain removes surface dirt from the exterior cabinet of your outdoor unit. It does not remove the layer of cottonwood fluff, grass clippings, pollen, and compacted debris that accumulates inside the condenser coil fins, the actual surface where heat transfer occurs. Because rain runs off the exterior without penetrating between fin rows where the fouling is physically located. Condenser coils consist of aluminum fins bonded to copper or aluminum tubing arranged in multiple rows, with fin spacing typically of 12 to 20 fins per inch. Airborne debris, particularly cottonwood seeds, which blanket large portions of the United States in late spring, accumulates between those fin rows, creating a matted layer that restricts airflow through the coil, regardless of how much rain falls on the outside of the cabinet. ASHRAE research on condenser coil fouling indicates that a coil with 10 to 30% airflow restriction experiences elevated head pressure, increased compressor discharge temperature, and reduced system efficiency of 10 to 30% depending on severity. Professional coil cleaning involves applying a chemical cleaner to the coil surface, allowing it to break down grease and biological adhesion, and rinsing from the inside out with low-pressure water. A process that removes material rain cannot dislodge because it lacks both the penetration angle and the chemical action. Landscaping practices significantly affect fouling rates. A unit surrounded by grass mowed with the discharge aimed toward it accumulates clippings in the coil consistently. Fouled condenser coils are the primary cause of high head pressure compressor operation, which is the primary cause of compressor overheating, which is the primary cause of premature compressor failure. Rain cleaning your condenser coil is like expecting a light shower to clean the inside of your car's engine bay. The exterior gets wet, the machine needs different tools. 42. Your programmable thermostat is too complicated. You have left the schedule unset, it runs at a constant temperature 24 hours a day, every day including all sleeping hours and all unoccupied hours. And you consider this a perfectly reasonable operating strategy that requires no adjustment from the technician currently looking at it. Running an HVAC system at a constant comfort temperature around the clock is the single most energy wasteful thermostat strategy available to a residential homeowner. And the Department of Energy has quantified exactly what this decision costs you. Setback strategies. Raising the cooling set point 7 to 10 degrees for 8 hours per day during sleeping and unoccupied periods. Save approximately 10% annually on the heating and cooling costs. For a household spending $2,000 annually on HVAC energy, this is $200 per year recovered from a one-time programming effort that most thermostats can accommodate in under 5 minutes using the setup guide included in the packaging. The physical basis for these savings is the rate of heat transfer between your home and the outdoors. A home maintained at 72 degrees when it is 95 outside has a 23-degree temperature differential driving constant heat flow into the building. A home allowed to rise to 82 degrees during those same hours has a 13-degree differential, 43% less driving force for heat infiltration, directly reducing the system's workload. Modern programmable thermostats include preset 5 2-day schedule templates requiring simple time and temperature adjustments. Smart thermostats eliminate the programming barrier entirely through learning algorithms and geofencing. Utility companies in many states offer demand response programs that reduce electricity rates in exchange for brief thermostat adjustments during peak demand. Programs that require smart or programmable thermostat enrollment and deliver $50 to $150 in seasonal bill reductions that are completely inaccessible to you while the thermostat runs at a single constant setting every hour of every day. The programming guide was in the box. 43. You looked up the part number on a consumer website, found a price significantly lower than what appears on the invoice, and have concluded the technician is padding the bill, because retail price is the correct reference point for evaluating a professional service invoice, and the gap between the two numbers is the amount being stolen from you. HVAC parts markup is a standard, disclosed business practice that reflects real costs. Technician time to procure the correct part, warranty liability on the installation, truck stock investment representing capital tied up in parts before a single call is dispatched, and the diagnostic expertise required to identify which specific part was needed in the first place. HVAC contractors purchase parts through wholesale distribution at prices below consumer retail, then apply a standard markup to cover overhead, warranty, and margin. Markup on HVAC parts typically ranges from 50 to 200% above wholesale cost, depending on part category, company overhead, and local market. And this is the standard model for all trades, not an anomaly created specifically to disadvantage you. The consumer price you found online is the retail price for a self-service customer with no warranty, no professional installation, and no diagnostic expertise, someone who already knows exactly what part they need, can install it correctly, and accepts full responsibility if the diagnosis was wrong and the part does not fix the problem. That is not the service being provided on this invoice. HVAC contractors maintain truck stock, inventory carried on service vehicles, representing $3,000 to $15,000 of capital investment per truck. This enables same-day repair rather than the multi-day wait that online ordering requires. Labor to install the part, typically embedded in flat-rate invoicing rather than listed separately, is also part of what you are paying for. Comparing a contractor's part price to an online retail price is like comparing a restaurant's steak price to the grocery store's and accusing the chef of fraud. One includes expertise, labor, and warranty. The other is just the raw material. 44. The outdoor temperature is a pleasant 68 degrees. You have declared the air conditioning off limits for the day and opened the windows in favor of free natural ventilation, and you feel environmentally responsible. And the technician mentioning outdoor dew point is being pedantic about something that clearly does not apply to a nice day like today. Outdoor temperature and outdoor humidity are separate variables that do not move together, and a 68-degree day with 85% relative humidity and a 64-degree dew point introduces more moisture into your home than the air conditioning would remove during the same period, directly and measurably undermining your indoor air quality and comfort. Dew point temperature is the key variable for indoor comfort assessment, not dry bulb temperature. A 68-degree outdoor temperature at 85% relative humidity has a dew point of approximately 63 degrees. Introducing this air into your home raises indoor relative humidity and can cause condensation on cool surfaces, including air conditioning supply diffusers and cold water pipes. A phenomenon that causes water damage and mold growth regardless of how pleasant the outdoor temperature felt when you made the decision. ASHRAE Standard 55 defines thermal comfort as a function of both temperature and humidity, and a space at 68 degrees and 80% relative humidity is outside the comfort zone for most sedentary occupants. It feels heavy and clammy despite the thermometer suggesting otherwise. In mixed humid climates covering the mid-Atlantic and portions of the Midwest, shoulder seasons regularly produce exactly these conditions. Mild temperatures paired with high humidity. Building science professionals in these regions specifically caution against window ventilation on high dew point days for this documented reason. The energy-saving alternative to opening windows is simply raising the thermostat set point slightly, not introducing uncontrolled outdoor air of unknown moisture content. Opening windows on a 68-degree day with a 64-degree dew point to save energy is like opening an umbrella indoors to stay dry. The temperature looked promising, the moisture did not cooperate. 45. Your carbon monoxide detector has alarmed intermittently over the past several weeks and then cleared on its own each time, and you have concluded the device is cheap, faulty, or overly sensitive. And you have mentioned this to the technician as a casual aside, while explaining 3 other complaints with the energy of someone describing a minor inconvenience rather than a documented exposure event. An intermittently alarming carbon monoxide detector is not a proven faulty detector until instrument testing confirms otherwise. It is a reported exposure event requiring immediate gas appliance inspection, beginning with the furnace heat exchanger, the most common residential source of carbon monoxide intrusion into the living space. Carbon monoxide is produced by incomplete combustion of carbon-containing fuels, including natural gas, propane, oil, and wood. Residential gas furnaces produce CO as a combustion byproduct that is normally vented to the exterior through the flue system. A cracked heat exchanger, the metal component separating combustion gases from the airstream, allows CO to enter the air distribution system and be delivered to occupied spaces through the same supply registers that condition your home. The CDC reports that CO poisoning causes approximately 400 unintentional non-fire deaths annually in the United States and accounts for over 100,000 emergency room visits. CO is colorless, odorless, and tasteless, entirely undetectable without an instrument. The detector is the only consumer-available detection method you have. CO detectors calibrated to UL 2034 standard alarm at 70 parts per million over 1 to 4 hours, 150 parts per million over 10 to 50 minutes, and 400 parts per million over 4 to 15 minutes. An intermittent alarm that clears is consistent with a fluctuating CO source, exactly the pattern produced by a heat exchanger that cracks under thermal load during specific operating conditions and partially seals during others. A heat exchanger inspection requires a combustion gas analyzer measuring CO in the airstream during system operation. Deciding a CO alarm is faulty because it goes off intermittently is like deciding a fire alarm is faulty because the fire goes out on its own sometimes. 46. Your air conditioning froze up. Visible ice on the refrigerant lines. And you have concluded this happened because you set the thermostat too low and pushed the system beyond its limits, and you would like the technician to confirm your diagnosis and probably agree that 68 degrees is more reasonable than the 64 you had been running. Evaporator coil freezing is caused by inadequate airflow across the coil, low refrigerant charge, or operation at low outdoor ambient temperatures, not by aggressive thermostat set points. The indoor temperature displayed on your thermostat is not the cause. The evaporator coil in a cooling system operates at refrigerant temperatures between 35 and 45 degrees Fahrenheit under normal conditions. It stays above freezing because warm indoor air pulled continuously across it by the blower transfers heat to the coil, keeping the surface temperature above 32 degrees. When airflow is reduced by a clogged filter, closed supply vents, or blower motor failure, the coil loses its heat source and drops below freezing, and condensate ice accumulates on the surface. A clogged air filter is the most common cause of freeze-up, and a system with restricted airflow will freeze at a 76-degree set point just as readily as at 64 degrees. Because the set point does not determine how much air moves across the coil. Low refrigerant charge causes low suction pressure, which corresponds to low refrigerant temperature, following the pressure-temperature relationship of the specific refrigerant in the system. When suction pressure drops below the saturation temperature threshold for 32 degrees, approximately 59 pounds per square inch for R410A, the coil surface freezes regardless of what number is on the thermostat. The correct response to a frozen coil is to shut off the compressor, run the blower on fan-only mode for 1 to 2 hours to melt the ice, and then diagnose the underlying cause before restarting. Blaming the set point for a frozen coil is like blaming the speedometer for a flat tire. The dashboard reading did not cause the condition at the wheel. 47. The technician came for a specific reported failure, repaired it, left, and subsequently a separate issue has emerged. And you are frustrated that the technician did not identify and preemptively repair every potential future failure during the initial visit, because now a second trip charge applies and the entire situation feels like it should have been handled in one visit. A service call is a response to a reported symptom. Identifying the cause and repairing it is the contracted scope of work. Predicting all future component failures across an entire mechanical system during a single diagnostic visit is not a realistic service deliverable and is not what was agreed to when you called. HVAC service calls are dispatched against a reported symptom: system not cooling, system not heating, system not starting. The technician diagnoses the reported condition, identifies the root cause, and performs the repair within that diagnostic scope. This is the standard service model for every trade. Comprehensive system inspections, where a technician measures every variable across the entire system and documents component health across all assemblies, are the function of annual preventive maintenance agreements, not emergency or diagnostic service calls. These are different products with different scope and pricing, and both are available to you. A technician who, during a capacitor replacement, identifies a marginal contactor and recommends proactive replacement is providing preventive advice above the minimum contracted scope. If you decline that recommendation, the subsequent contactor failure is a new event, not a misdiagnosis from a technician who told you it was borderline. The alternative model, requiring technicians to identify and replace every borderline component regardless of whether it has failed, would dramatically increase the cost of every service call and result in unnecessary replacement of parts that might have operated adequately for additional years. Being frustrated that the technician did not fix a part that was not broken during the call to fix a part that was broken is like being angry at the plumber for not replacing your water heater while he fixed the toilet. He fixed what broke. The other thing gets its own appointment. 48. You have dismissed the mini-split recommendation as basically a window unit, a portable, inferior, step-down option for people who cannot afford real central air conditioning, and you are not interested in having a wall-mounted device in your home because it looks like an appliance and you want a system. Ductless mini-split systems are technologically superior to window units in every measurable category: efficiency, noise level, temperature control precision, air quality features, and installation footprint. Comparing them to window units reflects unfamiliarity with the technology rather than an accurate assessment of what is being recommended. Mini-split systems use inverter-driven variable speed compressors that continuously modulate output between approximately 10 and 100% of rated capacity. Standard window units and most central air conditioning systems use single-stage compressors that operate at fixed output, fully on or fully off. Variable speed operation allows mini-splits to maintain temperature within half a degree of set point with significantly lower energy consumption at partial load, which is the operating condition for most of any given day. Efficiency ratings for modern mini-split systems range from 18 to over 30 CR2. Standard window units are rated at 10 to 12 EER. Most installed central systems fall between 14 and 18 CR2. Mini-splits represent the current efficiency frontier of residential cooling technology, not a compromise. The sound level of a mini-split indoor air handler at low speed operation is typically 19 to 26 decibels, quieter than a whisper. Window units operate at 50 to 65 decibels, the range of a normal conversation. Cold climate mini-split models from Mitsubishi, Bosch, Daikin, and Fujitsu deliver rated heating capacity at outdoor temperatures as low as -13 to -22 degrees Fahrenheit, covering the design heating day for most of the continental United States. The absence of ductwork also eliminates the 20 to 30% energy losses common in attic duct systems. Calling a mini-split a window unit is like calling a commercial kitchen oven a microwave. Both heat things. The technology difference is a generation. 49. You are prepared to tell the technician what refrigerant is in your system based on the color of the lines, which you identified from something you read. And you would like the technician to use this information rather than reading the nameplate, because you have already done that part. Refrigerant type cannot be determined by the color of the refrigerant lines, the color of the unit cabinet, or any visual observation of the installed system. Refrigerant lines are copper tubing insulated with foam rubber insulation, black or gray in color, regardless of what refrigerant is circulating inside them. The refrigerant is invisible within the copper. There is no visual correlation between line appearance and refrigerant type. The color coding convention that does exist applies to refrigerant service cylinders in a supply house or technician's truck, not to anything visible on an installed residential system. The air conditioning, heating, and refrigeration. Institute Color System assigns rose or pink to R410A cylinders, light green to R22 cylinders, sky blue to R134A cylinders, and specific colors to newer refrigerants, including R454B. These colors are on the service canisters. They are not on your house. Refrigerant identification on an installed system is accomplished by reading the unit nameplate, which is required by EPA and UL regulations to list refrigerant type and charge weight, and which is affixed to both the outdoor condenser and the indoor air handler. When a nameplate is missing or illegible, refrigerant type can be confirmed with a refrigerant identifier instrument that analyzes refrigerant composition by sampling from the system. Mixing refrigerants which occurs when a technician charges the wrong refrigerant into a system based on incorrect information, contaminates the entire refrigerant circuit and requires full system recovery, flush, and recharge to correct. This is an expensive mistake driven entirely by starting with incorrect assumptions rather than reading the label that is physically attached to the equipment. Identifying refrigerant type by line color is as accurate as identifying gasoline grade by the color of the fuel line under your hood. 50. You live in a region that sees cold winters. You have been told by someone whose information expired around 2005 that heat pumps stop working in cold weather, you want a gas furnace, and you are not interested in hearing about heat pumps because the person who told you this seemed very confident and also your neighbor agreed. Standard heat pumps do lose efficiency as outdoor temperatures fall. This is real, based on the compression ratio required to extract heat from cold air, and it gave heat pumps a legitimate reputation for cold weather inadequacy in the era before inverter compressor technology reached residential equipment. That era is over. Cold climate heat pump technology has advanced to a point where the original objection no longer applies to modern equipment, and the objection you heard was formed before the products that answer it existed. Cold climate heat pumps using enhanced vapor injection compressor technology, including the Mitsubishi Hyperheat series introduced in 2012, Bosch IDS 2.0, Daikin Aurora, and Fujitsu Halcyon cold climate models, maintain full rated heating capacity at 17 degrees Fahrenheit outdoor temperature and provide meaningful heating capacity at -13 to -22 degrees. These temperatures cover the design heating day for most of the continental United States outside of Alaska. The Northeast and Mid-Atlantic states, where average January temperatures range from 20 to 35 degrees, now have state energy office programs in Massachusetts, New York, Maine, and Vermont that include specific rebates for cold climate heat pump installation, reflecting the technology's validated field performance. The coefficient of performance of a cold climate heat pump at 17 degrees is approximately 2 to 2.5. Meaning the system delivers 2 to 2.5 units of heat for every unit of electricity consumed, compared to exactly 1 to 1 for electric resistance heating. Even at low temperatures, the heat pump is more efficient. The technology has moved. The objection is still standing in 2003. Dismissing heat pumps because it gets cold is like dismissing electric vehicles because it gets dark. 51. You keep all the interior doors in your home closed at all times for privacy and to keep different areas of the house at different temperatures. And you cannot understand why the master bedroom never reaches the set point while the hallway is always several degrees cooler. And you would like the technician to balance the system, which you assume means adjusting something on the equipment. Interior door position directly affects return air pathways in a central ducted HVAC system. Closed interior doors in rooms with supply registers, but no dedicated return grills create pressure imbalances that reduce system airflow, increase static pressure, and degrade overall performance. And this is not a coincidence specific to your home. Most residential HVAC systems use a centralized return air design, one or several large return grills located in hallways or central areas, pulling air from the entire home back to the air handler. Individual rooms receive conditioned supply air and are expected to return that air to the central return through the open doorway into the hallway. When you close the bedroom door and the room has a supply register but no dedicated return register, the room becomes positively pressurized as supply air enters, with no return pathway. This pressure imbalance forces supply air to exit through gaps around the door frame, window seals, and wall penetrations, often into attic or wall cavities rather than toward the return grill where it belongs. The pressurized room effect reduces effective airflow across the entire system, increasing static pressure and causing the blower motor to work against resistance it was not designed to operate against continuously. Building Science Corporation research documents interior doorway airflow transfer as a documented energy and comfort issue, and the DOE's Building America program includes it as a standard finding. The architectural solution is transfer grills or jump ducts that provide a return air pathway without requiring doors to remain open. Closing interior doors and expecting the HVAC system to perform normally is like closing half the return lanes on a highway and expecting traffic to flow the same way. 52. You have a genuine question delivered with the earnest curiosity of someone who really wants to understand how the system works. Where does the cold come from? You believe the air conditioning must contain some cold substance, ice, cold water, cold gas, that it uses to produce the cool air, and when the technician begins explaining the refrigeration cycle, you look skeptical because moving heat around does not sound like it could produce something as distinctly cold as the air coming from your registers. Air conditioning systems do not produce cold, they move heat. The refrigeration cycle extracts heat from your indoor air and rejects it outdoors, and the air that remains after the heat has been removed is cooler by comparison. Not because cold was added, but because heat was taken away. At the evaporator coil, liquid refrigerant at low pressure absorbs heat from your indoor air and evaporates into a gas. The indoor air, having transferred its heat to the refrigerant, is now cooler. The refrigerant is now warmer. The heat has changed location, from your air to the refrigerant. The compressor raises refrigerant pressure and temperature. The hot, high-pressure gas travels to the condenser coil outdoors, rejects that heat to the outdoor air, and condenses back to liquid. Your outdoor air becomes slightly warmer. Your indoor air is cooler. No cold was created at any point in this process. The concept of cold as a thing that can be produced and added to a space is a historical misconception that predates the development of thermodynamic theory. The caloric theory, which proposed that cold was a substance called frigoric, was disproven by experiments in the 18th and 19th century. The same refrigeration cycle operates in your refrigerator, your freezer, and industrial chillers. The scale changes. The physics does not. Asking where the cold comes from in an air conditioner is like asking where the darkness comes from when you turn off a light. Cold is not a substance the system contains. It is what is left when the heat is gone. 53. You have measured the supply air temperature at the register yourself using a cooking thermometer and would like the technician to use this reading to determine whether the refrigerant charge is correct, because the air is coming out at 68 degrees and you would like to know if that confirms the refrigerant is where it should be. Supply air temperature is one data point in a multivariable diagnostic system. It indicates that the system is producing some cooling. It cannot establish refrigerant charge, diagnose component health, or differentiate between the multiple distinct conditions that can produce any given supply air temperature reading. Refrigerant charge is evaluated through subcooling on the high side liquid line and superheat on the low side suction line, both measured with manifold gauges and temperature clamps correlated against manufacturer charging charts that specify target values at specific outdoor ambient temperatures and indoor wet bulb temperatures. Supply air temperature at the register appears nowhere in this diagnostic process. An undercharged system can produce 68 degree supply air while the compressor runs in conditions that cause long-term damage through inadequate mass flow and elevated discharge temperatures. An overcharged system can produce identical supply air temperatures while elevated head pressure and liquid refrigerant exposure threaten the compressor from a completely different direction. A dirty evaporator coil, restricted airflow, and correct refrigerant charge can produce the same supply air reading as a clean system with adequate airflow and deficient refrigerant. The identical output number masks entirely different system conditions, each requiring a different corrective action. Digital manifold gauge systems with wireless temperature sensors calculates target superheat and subcooling in real time and display whether the system is within proper charge range. A process requiring 15 minutes of steady-state operation and instruments that cost more than the cooking thermometer. The accuracy of those instruments is also relevant. A bimetallic cooking thermometer is typically rated at plus or minus 2 to 5 degrees. Professional HVAC digital thermometers used for delta T measurement are calibrated to plus or minus half a degree. The tool matters. Diagnosing refrigerant charge from supply air temperature is like diagnosing engine health from exhaust temperature. You learn something about what came out, you learn nothing specific about what produced it. 54. You adjusted the thermostat set point by 2 degrees, waited 90 seconds, stood in the middle of the room, felt no perceptible change, and have now concluded the system is not responding to thermostat input and needs to be looked at immediately. The thermal mass of your home, the combined heat storage capacity of all the air, walls, flooring, furniture, and structural elements, requires significant time and measurable energy to condition. A 2-degree set point change requires the system to remove a real quantity of heat from a real physical mass. This takes time, proportional to the system's capacity and the thermal mass it is working against, and that time is measured in minutes to tens of minutes, not seconds. A 2,000 square foot home with 8-foot ceilings contains approximately 16,000 cubic feet of air. Cooling this air volume by 2 degrees requires removing approximately 16,000 BTUs of sensible heat. A 2-ton central system delivering 24,000 BTUs per hour, under ideal conditions with no ongoing heat gain, requires a minimum of 40 minutes to accomplish this under those theoretical conditions, and longer in practice when accounting for continuous heat infiltration through the building envelope during the process. Human thermal comfort perception is also not instantaneous. The body's thermal comfort is a function of air temperature, mean radiant temperature of surrounding surfaces, humidity, air velocity, and metabolic rate. Wall and floor surfaces, which influence mean radiant temperature significantly, change temperature slowly, regardless of how quickly the air temperature shifts, meaning perceivable comfort change lags behind measurable air temperature change. Systems with variable speed blowers and variable speed compressors can respond faster to set point changes by increasing output, but even these are bound by the physics of moving heat out of a thermally massive structure. Thermostat response also includes a 3 to 5 minute compressor protection lockout that prevents rapid cycling. Expecting to feel a 2-degree set point change in 90 seconds is like expecting to feel the ocean liner change heading the moment you turn the wheel. 55. You purchased a second thermostat you wanted installed in the bedroom so you can have independent control over that zone, and you cannot understand why the technician is explaining a problem instead of simply connecting the wires. Because 2 thermostats should logically provide more control than 1, and the logic feels airtight. A standard single-zone HVAC system can only accept control input from 1 thermostat at a time. Installing a second thermostat on the same zone, wiring creates a parallel control circuit where 2 independent switches can simultaneously energize or de-energize the system with no resolution logic in the equipment to determine which one takes precedence. The behavior of 2 parallel thermostats on a single-zone system includes one thermostat satisfied while the other is still calling, causing the system to cycle on and off rapidly as the 2 sensors alternate control. And voltage backfeed from one thermostat's power terminal into another's control terminals, which can damage the control board in ways that cost $300 to $800 to correct. True multi-zone control in a ducted HVAC system requires a dedicated zoning panel, a specific control board that accepts input from multiple thermostats and independently operates motorized dampers in the ductwork to direct conditioned air to whichever zone is calling for it. This is a designed, engineered, commissioned system configuration, not something achieved by adding a second thermostat to existing wiring. Ductless mini-split systems provide exactly the room-by-room control you are describing natively, with each indoor air handler operating its own independent refrigerant circuit with its own control. Ecobee's room sensor system provides multi-room temperature awareness through a single thermostat that averages or prioritizes specific room temperatures during occupancy, a legitimate single thermostat solution. Installing a second thermostat to control a single-zone system is like installing a second steering wheel for the passenger. Both are connected. Neither knows what the other is doing. The vehicle responds to whoever grabs hardest, and eventually something breaks. 56. You can smell something when the furnace runs. You have identified the smell as gas. You have been running the furnace with a background sense of unease about this for several weeks, and you are mentioning it to the technician now while also asking about thermostat calibration. As though the 2 concerns are roughly equivalent in urgency, natural gas is odorless in its natural state. The smell you associate with gas is mercaptan, ethyl mercaptan or tertiary butyl mercaptan, added by gas utilities at approximately 1 part per million specifically to make leaks detectable by human smell at concentrations well below the lower explosive limit of 5% gas in air. A properly operating gas furnace combusts natural gas in a sealed heat exchanger, and during normal operation, no uncombusted gas should be present in your living space at any detectable concentration. If raw mercaptan smell is present during furnace operation, it indicates a gas supply leak upstream of the furnace, a failed gas valve, incomplete combustion with gas spillage, or a cracked heat exchanger allowing combustion gases to enter the air distribution system, none of which are minor calibration adjacent concerns. The smell most commonly reported as gas smell during the first furnace cycles of the heating season is actually burning dust. Dust accumulated on the heat exchanger and burners during the off-season combusting at first light-off. This produces a brief, distinctive smell that dissipates within a few cycles and is not a gas leak. A mercaptan smell that persists beyond startup or that is detectable away from the furnace location requires a specific response. Evacuate the space, avoid operating electrical switches, and call the gas utilities emergency line from outside the building. A combustion gas analyzer measuring CO in the airstream during operation provides definitive answers that nose-based diagnosis cannot. Deciding a CO alarm is faulty because it clears on its own, and deciding a gas smell is probably dust are two versions of the same dangerous conclusion: skipping. Both deserve instruments before opinions. 57, you are getting multiple quotes and you have decided all HVAC brands are the same product differentiated entirely by marketing. The cheapest option is therefore the correct option, and any contractor suggesting otherwise is trying to upsell you on a distinction that does not exist in the actual equipment. HVAC equipment brands differ meaningfully in compressor technology, warranty terms, parts availability, dealer network quality, efficiency ranges, advanced features, and documented reliability outcomes. And these differences are measurable, not theoretical. Compressor technology varies significantly between manufacturers and product lines. Scroll compressor designs from Copeland, used by Carrier, differ in engineering tolerances and documented reliability from Panasonic rotary compressors used in some Mitsubishi configurations and Toshiba BLDC compressors used in other premium applications. Independent reliability research, Consumer Reports, Annual Appliance Reliability Surveys, and J.D. Power HVAC customer satisfaction studies consistently shows statistically significant differences in brand reliability and owner satisfaction. These are survey datasets of actual owner experiences over years of operation, not manufacturer claims. Warranty terms differ in ways that matter. Standard warranties range from 5-year parts to 10-year parts with 10-year compressor coverage. Some manufacturers offer lifetime heat exchanger warranties on furnaces at certain product tiers. Others offer 20-year heat exchanger coverage. These are real financial differences that materialize when something fails in year 8. Parts availability and dealer network density matter operationally. A brand distributed widely through multiple supply houses ensures parts are available same day or next day. Niche or limited distribution brands may require multi-day or multi-week lead times for specific components. Smart home integration, remote monitoring features, and proprietary communicating system platforms vary widely. Carrier's Infinity system, Trane's ComfortLink 2, and Lennox's iComfort are not interchangeable with each other's components. Treating HVAC brands as interchangeable because they all have compressors and coils is like treating car brands as interchangeable because they all have engines and wheels. The nameplate is where the similarity ends. 58. You are replacing an existing system and you have asked the technician to simply match the size of what was there before or estimate from the square footage because a full manual J load calculation sounds like an unnecessary step for a straightforward equipment replacement in a house that already had HVAC. Rule of thumb sizing, 400 square feet per ton or match what was installed previously, is the primary cause of HVAC oversizing in American homes. And oversizing produces the short-cycling humidity problems and accelerated equipment wear that generate the comfort complaints you spent the last system's entire lifespan filing. The 400 square feet per ton rule was developed as a rough screening tool for preliminary estimates in specific geographic and construction contexts. Applied universally across climate zones, construction vintages, and building configurations, it produces sizing errors of 30 to 50% in both directions, resulting in systems that are dramatically too large or dangerously too small for the actual load. Matching what was there previously assumes the previous system was correctly sized. An assumption that Energy Star research contradicts, having found that a significant percentage of installed residential systems are oversized, some by a full ton or more. Replacing an oversized system with the same size perpetuates the problem and may void the Energy Star certification of the new equipment. Building conditions also change between original installation and replacement. Insulation may have been added, windows replaced with better performing units, air sealing improved, all of which reduce the calculated load. A home that required a 4-ton system in 1998 may correctly require a 3-ton system today. Manual J software approved by ACCA can be completed for a standard residence in 2 to 4 hours. Several state energy codes, including those in California, Florida, and various New England states, require a documented manual J calculation as a condition of permit issuance for HVAC replacement. Sizing a system by rule of thumb is like prescribing medication by body weight with no other diagnostic information. It might be close enough for a textbook average. It is not engineering. 59. You have positioned your outdoor condenser unit facing the southern exposure because heat pumps pull heat from outdoor air, and more sun exposure means more heat available, and therefore the unit should perform better in winter heating mode because you have maximized its access to solar energy. and you are genuinely surprised that the technician views this as a concern rather than a thoughtful optimization. Condenser unit placement in direct sun increases the ambient temperature the unit must work against during summer cooling operation, reducing efficiency across the season when cooling demand is highest and run hours are longest. ACA and equipment manufacturer installation guidelines specify that outdoor condenser units should be located in shaded areas where possible, driven specifically by cooling season efficiency considerations. During summer cooling, the condenser rejects heat from indoors to the outdoor air, and the efficiency of that heat rejection is a function of the temperature differential between the refrigerant and the outdoor air. A unit in full afternoon sun on a 95-degree day may experience effective ambient temperatures at the coil surface of 105 to 115 degrees due to solar radiation on the cabinet and surrounding ground, dramatically increasing the compression ratio required and reducing efficiency by 5 to 10% across peak cooling hours. The winter heating benefit of sun exposure is real but marginal. Solar radiation on the outdoor coil can raise its effective temperature slightly during daylight hours, but heat pump heating systems are designed for nighttime design conditions, when the sun is absent and temperatures are at their lowest. The benefit is present for perhaps 4 to 6 hours per day under ideal winter conditions. The correct approach to condenser placement optimization is a shade structure, a pergola, fence, or deciduous tree that blocks summer afternoon sun while maintaining adequate airflow clearance on all 4 sides and allowing winter sun exposure. Aiming your outdoor unit at the sun to improve heating performance is like parking your car in the sun to warm the interior faster in January. It works briefly, creates a larger problem in summer, and was not what the installation manual described. 60. Your digital thermostat has been displaying a low battery warning for several months. You have ignored it because you know the thermostat is wired to the HVAC system and cannot possibly depend on batteries to function. And you have called today because the system has stopped responding to commands, which you are treating as an equipment malfunction rather than the conclusion of a months-long warning you chose not to act on. Many digital and programmable thermostats use batteries as the primary or backup power source for the microprocessor, display, and memory functions, even when wires are connected. And a dead battery causes the thermostat to lose its programmed schedule, fail to send control signals, or shut down entirely. Thermostat power configurations fall into 3 categories: battery-only devices with no continuous power from the HVAC system, C-wire powered thermostats with battery backup for memory and display, and C-wire powered thermostats with no batteries. The wires connected to your thermostat are control signal conductors. They carry the 24-volt signal that activates heating or cooling when the thermostat calls for it. In many older programmable thermostats, these wires do not provide continuous power to the thermostat itself. The device runs entirely on batteries, and when the batteries fail, it goes dark, regardless of how many wires are attached to the back. When thermostat batteries fail, the most common symptoms are a completely dark display, loss of programmed schedule with the system defaulting to a fixed set point or no calls at all, and intermittent system response that appears to be equipment malfunction. Thermostat battery replacement costs approximately $3 to $5 and takes 2 minutes. It is the single lowest cost, highest probability diagnostic step for an unresponsive thermostat and should be attempted before any service call is placed. Assuming your thermostat does not need batteries because it has wires is like assuming your smoke detector does not need batteries because it is hardwired. Some are not. The blinking warning light was communicating this distinction clearly for months before you called. 61. Your system is short cycling and you have concluded the thermostat is in a bad location. It must be reading the wrong temperature, satisfying too early, and moving it to the bedroom will solve the problem. And you have presented this as your diagnosis before the technician has connected a single instrument to the system. Thermostat location can cause short cycling in one specific scenario. The thermostat is mounted directly in the path of supply air from a nearby register. The cooled supply air reaches the sensor before the occupied space is adequately conditioned, and the system shuts off prematurely. This is a legitimate installation problem that typically manifests from the initial installation, not suddenly in a system that has run normally for years. Short cycling has a differential diagnosis with multiple root causes, and thermostat location appears on that list alongside oversized equipment, frozen evaporator coils, failed capacitors causing compressor thermal overloads, high head pressure safety switch trips from dirty condenser coils, and low pressure switch trips from deficient refrigerant charge. Oversized equipment is the most common cause of persistent short cycling. An oversized system satisfies the thermostat quickly regardless of thermostat location because it simply has more cooling capacity than the load requires. Relocating the thermostat to a position that satisfies more slowly extends cycle time without correcting the fundamental capacity mismatch, meaning you have moved a sensor and left the actual problem in place. A capacitor failure causing the compressor to trip its thermal overload, a high head pressure switch tripping because the condenser coil has not been cleaned in 4 years, and a low pressure switch tripping because the system has been slowly losing refrigerant. None of these respond to thermostat relocation. The correct diagnostic sequence begins with instruments measuring electrical draw, refrigerant pressure, and airflow, not with moving hardware based on a theory formed before any measurements were taken. Moving the thermostat to fix short cycling without a prior differential diagnosis is redecorating around a structural problem. The room looks different. The problem is still in the wall. 62. Air duct cleaning is a scam. There's nothing in your ducts. You have never had them cleaned. Everything is fine, and the technician raising it as a consideration is either in on the scam or has been fooled by it. And you would like to move on to the actual issues. Duct cleaning is not categorically a scam, but it is also not a universally necessary service with a fixed schedule applying to every home regardless of history. The EPA's official guidance on residential air duct cleaning documents specific conditions under which cleaning provides real benefit: visible mold growth on ductwork or HVAC components, evidence of rodent or insect infestation in ducts, or confirmed excessive debris accumulation being discharged into living spaces. The EPA explicitly does not recommend cleaning as a routine maintenance measure in the absence of these conditions, which is a statement that both validates the service and defines its appropriate scope. What gives duct cleaning its scam reputation is the portion of the industry that performs it without meeting the INADCA standard, the National Air Duct Cleaners Association's ACR standard for assessment, cleaning, and restoration, which requires negative pressure vacuum collection at the source while agitating duct surfaces with contact cleaning tools. Blowing air through ducts, fogging with deodorizers, or vacuuming superficially at the register face is not effective cleaning and is the direct source of the industry's credibility problem. Conditions that legitimately call for duct cleaning include recent renovation or construction that generated dust inside the duct system, prior water intrusion confirmed by inspection, visible biological growth on duct surfaces, or documented rodent activity with physical evidence. A home that has never been renovated, uses adequate filtration consistently, has well-sealed ducts, and has no documented water or pest history may genuinely not need duct cleaning. The category is legitimate. Your specific situation determines whether it applies. Deciding duct cleaning is always a scam is like deciding car detailing is always a scam. It can be. It is also a real service with real value when the conditions call for it and the company doing it knows what they are doing. 63. You have been running the heat briefly during summer to dry out the HVAC system, reduce mold, and improve air quality. A maintenance practice you developed from something you heard. And you would like the technician to confirm this is beneficial before they proceed with the actual service visit. Running heat mode briefly in summer does not meaningfully dry out your HVAC system. It reverses refrigerant flow in heat pump configurations, warms the occupied space unnecessarily, consumes significantly more energy than cooling operation, and provides no documented benefit that addresses the actual sources of moisture accumulation in HVAC systems. The moisture in your HVAC system resides primarily on the evaporator coil surface, in the condensate drain pan, and in the drain line, components that are not dried by running heat mode because the heat strips or heat pump heating mode do not pass air through the indoor evaporator coil in a configuration that would evaporate residual moisture from that surface. In a heat pump system, activating heating mode reverses refrigerant flow through the reversing valve. The outdoor coil becomes the evaporator and the indoor coil becomes the condenser. This effectively bypasses the indoor evaporator, which is the moisture accumulating component, because in heating mode, that coil is no longer functioning as an evaporator. Running heat cannot dry the evaporator coil because the evaporator coil is functionally on the outdoor unit in heating mode. Electric resistance heat strips also do not pass air through the evaporator coil in a drying configuration. The air flows across the heating elements, not back across the cold, wet coil surfaces where moisture lives. The correct approaches to reducing evaporator coil moisture accumulation are UVC germicidal lamp installation to prevent microbial growth, coil cleaning with a registered antimicrobial coil cleaner, and ensuring the condensate drain runs freely. Running heat in summer to dry the system is thermally backward and spatially incorrect. You are heating the rooms, the moisture is on the coil, these are different locations. 64. Your outdoor condenser unit is visibly tilted on a deteriorating pad. The technician has noted it needs to be leveled, and you have dismissed this as unnecessary because it is just sitting on a surface, and precision leveling seems like the kind of detail that matters for surgical equipment, but not for a machine sitting in your backyard. Outdoor condenser units must be level within manufacturer set specifications for compressor lubrication, condensate drainage, and vibration management. And these are engineering requirements documented in every major manufacturer's installation manual, not aesthetic preferences invented by technicians with time to spare. Compressor oil lubricates the internal moving parts of the compressor through a combination of pressurized oil feed and refrigerant-carried oil. Proper lubrication depends on the compressor being mounted within the manufacturer's specified levelness tolerance, typically within 5 degrees of vertical. An unlevel compressor can cause oil to pool away from critical lubrication surfaces, resulting in metal-to-metal contact and accelerated wear that develops gradually and invisibly until the compressor fails. Manufacturer installation manuals for Carrier, Trane, Lennox, Rheem, Goodman, and all other major brands include explicit levelness specifications and instructions to verify with a spirit level during installation and after any pad settlement. Heat pump systems in heating mode produce condensate on the outdoor coil that must drain freely from the coil and base pan. An unlevel unit pools condensate in a low corner, creating conditions for ice bridging across the coil base that impairs operation and can contact the fan blade. Vibration in an unlevel compressor transmits to the refrigerant lines, fatiguing brazed joints over time and creating leaks at locations entirely consistent with vibration-induced metal fatigue. Concrete pads crack and settle, particularly in regions with clay soil that expands and contracts seasonally. An initially level installation can become unlevel over years without any single dramatic event. The fix ranges from shimming with composite shims to replacing a deteriorated pad, both of which are simple and inexpensive relative to the compressor damage unlevel operation causes over years. Leaving your outdoor unit tilted because it is just sitting on a pad is like leaving your washing machine unlevel because it is just sitting on the floor. 65. You time the technician. You have watched HVAC repair videos where capacitors are swapped in under 10 minutes. You presented a 20-minute benchmark when they arrived, and you are now at 45 minutes with visible impatience and a request for an explanation of every additional minute. GPX diagnostic and repair time is determined by the complexity of the failure, the system configuration, the diagnostic process required to confirm the root cause, and the physical conditions of the specific installation, not by the fastest possible execution of the most straightforward version of any given repair in a controlled setting filmed for a video. A capacitor replacement that takes 10 minutes in a video involves a system where the failed component was pre-identified before filming began, the unit is easily accessible, the terminals are unobstructed, and no additional diagnostic steps are required because the scenario was already confirmed. Real-world variables that extend this include a capacitor located behind a control board that must be carefully removed first, a dual-run capacitor where one section reads marginal and the other has failed, or a system where the capacitor failure is the symptom of an underlying high amperage condition requiring additional diagnosis to prevent the replacement from failing within a week. Proper HVAC service also includes verification after the repair. The technician must run the system through a full cycle, measure operating parameters at steady state, including discharge pressure, suction pressure, delta T, and compressor amperage, and confirm all safety devices are operational. This verification requires 15 to 30 minutes of system runtime after the repair is complete. Time that appears unproductive to an observer standing next to the unit, but is essential to confirming the repair actually solved the problem rather than just appearing to. The HVAC industry uses flat rate pricing for most repairs, specifically to decouple the customer's perception of time from the invoice total. Under flat rate pricing, the technician's time does not change what you pay. Timing your HVAC technician against a YouTube video is like timing your surgeon against the fastest recorded version of the procedure. The video was clean, controlled, and pre-diagnosed. Your system is real. 66. Your comfort complaints and your high energy bills are an HVAC problem. The solution is in the equipment, and the technician suggesting attic insulation feels like a deflection. a way to redirect responsibility away from the system and toward a building problem that is not what you called about today. Attic insulation directly determines how much heat flows into your home through the ceiling plane, the largest exposed surface area in a residential structure. And improving it is frequently the single highest return action available for reducing HVAC energy consumption, often outperforming equipment upgrades in homes where the building envelope has not been addressed. The attic ceiling in a 2,000 square foot single-story home represents approximately 2,000 square feet of surface area through which heat transfers continuously between the conditioned living space and the unconditioned attic above it. Attic temperatures in southern climates routinely reach 130 to 150 degrees Fahrenheit in summer. The temperature differential between a 150-degree attic and a 72-degree living space is 78 degrees. With R13 insulation, common in older homes, heat flow through that ceiling is dramatically higher than with R38 or R49 insulation, and the HVAC system must remove all of that conducted heat continuously while it flows in from above. DOE and Energy Star research quantifies the energy savings from attic insulation upgrades, finding that increasing attic insulation from R11 to R38 in a southern climate home can reduce heating and cooling energy consumption by 15 to 30%, a range comparable to replacing a 10-SEER system with a 14-SEER system, and in many cases achievable at lower installed cost. The interaction between attic insulation and ductwork is direct. Ductwork located in a poorly insulated attic gains heat from the surrounding environment regardless of the duct insulation quality, adding load that the system must then overcome. Ignoring attic insulation to focus on the HVAC equipment is like upgrading your car's engine while leaving the windows open on the highway. The engine is working harder than it needs to because the environment it operates in has not been addressed. 67. You have a heat pump, the thermostat has an emergency heat setting, it is February, it is cold outside, and you have switched to emergency heat because that is clearly what the setting is for. Cold weather emergencies, like the current situation of it being February. And your energy bill for the month has arrived and you have questions. Emergency heat mode disables the heat pump compressor entirely and runs only the electric resistance backup strips, making it the most energy inefficient heating mode available on a heat pump system. It exists for one specific scenario. The heat pump itself has mechanically failed and the compressor cannot operate, leaving the resistance strips as the only remaining heat source. It is not a cold weather performance enhancement, and it is not for February. Heat pump systems include electric resistance backup strips, typically rated at 5 to 20 kilowatts depending on system size, which heat air through direct electrical resistance with a coefficient of performance of exactly 1.0. Every watt of electricity consumed produces exactly 1 watt of heat, identical to an electric space heater and no more efficient. The heat pump compressor operating in heating mode delivers 2 to 4 times more heat per unit of electricity by moving heat from outdoor air rather than generating it, with a coefficient of a performance of 2 to 4 depending on outdoor temperature. Emergency heat mode activates the strips while simultaneously locking out the compressor. You are achieving the same heating output at 2 to 4 times the electrical consumption. Auxiliary heat, labeled AUX heat on most thermostats, is the correct cold weather mode. It activates the resistance strips in addition to the running compressor when the heat pump alone cannot meet the demand, and it engages automatically without any input from you. The thermostat manages this transition. Your job is to set a temperature, not to select a mode based on the outdoor conditions. Utility companies in heat pump service territories document emergency heat misuse as a leading cause of unnecessarily high winter bills, so consistently that many thermostat manufacturers added explicit warning labels to the setting. Save emergency heat for the actual emergency. 68. You purchased a new construction home. The HVAC system was installed as part of the build. It is brand new, and any comfort complaint is there for the home settling or your adjustment to a new space, because a newly installed system is by definition correctly installed and operating as designed, and the technician suggesting otherwise is being contrarian. New construction HVAC systems have among the highest rates of sizing errors, installation defects, and commissioning failures in the residential market, and new and correct are entirely different attributes that do not automatically coincide. Energy Star and ACCA research has found that a majority of new construction HVAC systems are improperly commissioned after installation, meaning the installed system was never verified to be operating within design parameters. Common unverified items include refrigerant charge, airflow balance across all registers, duct leakage rate, and equipment sizing validation against a proper load calculation. New construction creates specific contamination conditions. Drywall dust, wood shavings, paint particles, and insulation fibers generated during construction enter the duct system through uncovered openings during the building phase, loading new filters rapidly, fouling new evaporator coils, and potentially entering blower assemblies before the first homeowner ever adjusts a thermostat. HVAC systems in new construction are frequently sized using simplified estimation methods rather than full manual J calculations, because production builders working under cost and schedule constraints may use abbreviated approaches. Duct systems in new construction are installed by subcontractors under production schedule pressure, and duct leakage rates in new construction systems measured by independent testing programs are frequently higher than in retrofitted systems. The new home warranty period, typically 1 year for systems defects, 2 years for mechanical, 10 years for structural in most states, is the window for documenting HVAC performance deficiencies with legal remedy available. Homeowners who accept poor performance as new home adjustment may lose this window entirely. Assuming new construction HVAC is correct because it is new is like assuming a new restaurant is serving great food because the kitchen equipment is brand new. The equipment being new says nothing about whether the engineering, the installation, or the commissioning was done correctly. 69. Your utility bills have increased significantly, your HVAC system appears to be running, and you have concluded the utility company is billing you incorrectly. So you are pursuing a meter dispute while the HVAC system continues to run in whatever degraded state it is actually in, because the meter feels like the more actionable complaint. Utility meters are calibrated, inspected devices subject to accuracy standards set by state public utility commissions, with ANSI C12 standard specifying residential meter accuracy tolerances of plus or minus 2%. Meter errors significant enough to produce the billing increases customers typically dispute are rare and are flagged immediately by utility billing algorithms that monitor for anomalous consumption patterns. The meter dispute process, available to all customers, involves the utility performing a formal test, and the statistical outcome of these tests overwhelmingly confirms meter accuracy. When errors are found, the utility is legally required to retroactively correct billing. HVAC system efficiency degradation is cumulative, invisible to casual observation, and measurable against historical billing data. A condenser coil with 15% fouling, a refrigerant charged 10% low, and a blower motor running at 85% of rated airflow due to a partially clogged filter represents 3 separate simultaneous efficiency losses that together can increase cooling energy consumption by 25 to 40%. The system appears operational, the efficiency is gone. Smart meter data, now available to customers through utility web portals in most service territories, provides hourly energy consumption that can be correlated directly to HVAC operating hours. An HVAC system running longer per degree of cooling delivered is demonstrably losing efficiency, and this is visible in the data without requiring any specialized instruments. The correct response to a high bill is to request the utility's formal meter test for peace of mind and simultaneously schedule an HVAC efficiency evaluation for the more likely explanation. Both can run in parallel. One will almost certainly provide the answer. Blaming the utility meter for your energy bill without checking the HVAC system is like blaming the gas pump for your fuel costs without checking whether your tires are flat. 70. You can hear the system running. You can feel air from the vents. The outdoor unit is on, and you are confident the system is cooling. Which makes the technician's concern not just unnecessary, but mildly offensive, because you used direct sensory observation and it told you the system was operational. An HVAC system can run, producing audible operation and detectable airflow, while delivering zero or negligible net cooling to your occupied space, and running and cooling effectively are not the same condition. Multiple distinct failure modes produce a running system that provides no useful cooling whatsoever, and none of them are detectable by standing near a vent. A completely frozen evaporator coil produces this exact scenario. The outdoor unit runs, the blower runs, air comes from the registers, and the evaporator coil is encased in ice, blocking all meaningful heat transfer. Air passing through the air, handler bypasses the ice-covered coil or passes through a small unfrozen section and arrives at the registers at near ambient temperature. The system runs continuously and cools nothing. A failed reversing valve on a heat pump stuck in heating mode means the compressor runs, both fans operate, air flows from every register, and the system is delivering warm air into an already warm space, potentially raising indoor temperature while you believe it is cooling. A compressor with failed internal valve assemblies may run audibly. The motor turns, the unit sounds operational, while producing no significant refrigerant compression and therefore no refrigerant circulation and no BTU transfer in either direction. This is identifiable only through refrigerant pressure measurement showing near equal suction and discharge pressures. Significant duct leakage can cause the system to run continuously, while 40 to 50% of conditioned air is delivered to the attic rather than to the living space, and the home never reaches the set point. The delta T measurement, supply air temperature minus return air temperature, is the minimum field verification of actual cooling delivery. Confirming your system is cooling because you can hear it running is like confirming your car is moving because you can hear the engine. The engine is on. Whether you are going anywhere requires looking out the window. 71. The technician completed the service call, confirmed the system was operating within manufacturer's specifications, handed you an invoice, and you have concluded that because no parts were replaced and the explanation involved technical language, nothing was actually done and the fee is unjustified. Because visible replaced components are the only evidence of legitimate work. Diagnosis is a skilled professional service with quantifiable value, and a correctly functioning system confirmed by instrumented measurement is a service outcome, not an absence of work. An HVAC diagnostic service call involves a trained, EPA-certified technician using calibrated instruments to evaluate a system's operating condition against manufacturer specifications, measuring refrigerant pressure, testing electrical draw, assessing airflow, measuring temperature differential, and verifying safety device function. This process takes 30 to 60 minutes for a thorough evaluation and requires instruments costing $1,000 to $5,000 and field experience built over years of working systems. The scenario where no failed component is found and the system is operating correctly is the specific and valuable diagnostic conclusion. It rules out refrigerant issues, electrical failures, mechanical failures, and controls problems simultaneously, and may redirect the investigation toward building envelope deficiencies, occupant behavior patterns, or expectations that do not match system design, all of which are also legitimate and useful diagnostic findings. Technicians who perform maintenance actions without producing a visible replaced part, cleaning electrical contacts, tightening connections, clearing a partially restricted condensate drain, verifying and documenting refrigerant charge within specification are performing legitimate services with a real preventive value. The expectation that a service call must produce a tangible replaced component to justify its fee applies the same logic that would question a physician's invoice for an exam that found nothing seriously wrong. The absence of a finding is itself a finding, and it required expert evaluation to produce it. The invoice itemization documents what occurred. A reputable contractor can explain every line in terms you can follow if you ask. You paid for expertise, not theater. And expertise sometimes concludes that the thing you were worried about is not the problem. If you want to see more, click the video on screen now.